All right, can you hear me? Lots of people out there. It's going to be fun. Well, welcome to the third annual Air Toxins under the Big Sky High School Symposium. And I can give you a little bit of history of this thing. We started with one student sampling in the homes of 14 other students from Big Sky High School in 2002. And if you look around you now, I'd say the program's grown just a little bit. We have universities coming from the Northwest Indian College. We have 2 other high schools. We have representatives from Libby High School as well. So it's lots of energy in this room, and it's going to be fun. So let's make the most of it today. No stress, right? So again, welcome to the University of Montana. And I was going to go through the schedule, but you guys should all have a copy of that. We're a little behind already, so we're going to just cut right to it. It's going to be fun. Like I said, this is we like to think of this as the Super Bowl of the Air Toxics program. So you guys have put a lot of work into this, a lot of time, a lot of heartache, probably thinking, what in the heck am I doing this for? But this is our way of saying thank you for participating in the program, and we hope to make this as fun as possible for you guys. So we have free swag at the end. Keep that in mind when you're stressing out right before your presentation. But everybody's in the same boat, right? So it's okay to be a little bit nervous. Look around you. Everybody has to present, so it's going to be a lot of fun, okay? So without further ado, I'd like to invite Dr. Garen Smith up to give a keynote address. So Garen is a chemistry professor, environmental chemistry, analytical chemistry professor here in the Department of Chemistry. He arrived here in 1991. And he's involved in lots of different stuff. I can honestly say he's the busiest guy that I know. And how many guys have actually seen him do his wizard presentations in the school? Okay. He gets around. So he's also involved with a lot of cool research with air pollution, figuring out what the sources of air pollution are and how to fix those sources. Works a lot with the state governments, the county governments. And he was the reason that I came to Missoula in 1997 to go to graduate school. And he also has an alter ego named Gee Whiz, which you'll see, I assume, in a little bit later. So please give it up for Garen Smith.
Well, thank you, Tony. I'm thrilled to be here today. And part of what I wanted to do is give you about a 10-minute history of how we've worked on the Missoula Airshed. Not only do I work here at the university, but I'm the chairman of the Board of Health and the Air Pollution Control Board. So we try to take the best science that we know and come up with ways that we as a community can try to make the air better. We're still not home free, and so what I wanted to do is give you a little bit of history of where we've been and why what you're doing is so important to us doing better. So a lot of times when I go out of town, out of state, and talk about things that I work on, people say, why are there air problems in Montana? It's a huge state and there aren't many people around. How come you have air problems? Well, there's sort of a combination of 2 factors that lead us to air problems. First of all, although there aren't a whole lot of us, we tend to clump together in population centers where we bring together cars, homes, and businesses, which are sources of emissions. And then we put these population centers right in the bottom of mountain valleys, and these mountain valleys are subject to frequent overnight temperature inversions. So I'd talk a minute about mountain valley problems. If you go to DEQ's website and look for air pollution information, you can see the cities that they report on. And it's not an accident that all the places that they report on are in the west, situated at the bottom of mountain valleys. So that's where we have these inversion problems. Now, maybe Russ will find things that are wrong with my meteorology here, but we have unstable air and stable air. So unlike personalities, unstable air is good. Unstable air means good mixing. That's when we have warm air on the bottom, which is lighter and more buoyant, and cold air over top. This is the normal situation. As you go up the mountainside, the air gets colder. How does that lower layer get warmed up? Well, sunlight gets absorbed by the soil. It heats the air at the bottom of the valley, and then it sets up convectional cells that the hang gliders and the eagles like, and any pollutants that are released get wafted upwards where they can be carried off by the winds aloft to Great Falls, right? Well, stable air or stagnant air, when we have inversions, oftentimes sets up overnight because the cold air is denser, it sinks to the valley bottom. So we have cold on the bottom and the warmer air is up on top. Cold air being heavier doesn't want to go anywhere, so it sets up a thermal boundary. And the colder it is, sometimes the more tightly that gets compressed. This is exacerbated in the winter by low sun angles so that the soil doesn't heat up, and if we have snow or ice around, the sunlight reflects instead of being absorbed to warm up that bottom layer of air, so these inversions stick around for a while. Any pollutants that are released get trapped in the valley. I stole this picture from Emily's presentation, but it's a nice depiction of an inversion layer sitting in Missoula. You can see a very distinct cloud deck level there that's caused by that cold air puddle at the bottom of the valley. So what do we worry about in ambient air? Ambient air is our technobabble for public air spaces. Really, we have a fairly short list. Missoula's been sort of chronically plagued by two things on the list: carbon monoxide and particulate matter. The PM10 means 10 microns or less. Because of that, because we were not in attainment with the Clean Air Act, we had to put together a regulatory body called the Air Pollution Control Board, and that's the board that I currently chair. And we have regulatory authority to try to pass regulations and help launch educational campaigns to do better with our airshed. Here's the list of what's regulated in Missoula as of 2006. It hasn't changed, so this is what's regulated in 2007. What's going to be of prime importance to us in the near future is PM 2.5. I'll talk to this. The former level was 65. They cut it almost in half, and we're going to have trouble meeting that. And that's where some of your work is going to help us out. I thought I would show how well we've done with the first of those pollutants that have plagued us, which is carbon monoxide. Ben Schmidt, who's with the health department and is standing back there next to Tony, in 1990 determined that 64% of carbon monoxide was coming from vehicle tailpipe emissions, 26% from stoves, about 10% from industry. This has to be measured at the worst point in the airshed, which is Malfunction Junction, which is why if you sit at Brook South Russell and look at the corner of the fairgrounds, you'll see the little white trailer that says Carbon Monoxide Monitoring Station. We've been doing well. If you look at the data on the worst days since 1988, we've been getting better with respect to carbon monoxide. Even though the valley population has been growing, the standard nationally is 9 parts per million on an 8-hour average, and you can see we've been well below that since 1991. We asked, as a board, we asked the health department to do a more recent study because that 1990 study was before North Reserve existed at all. So Ben, again, who's standing back there, did some studies during the winter of 2005 and 2006. When the weather looked like we were going to have stagnant air conditions, he put up monitors around the city. Here was December 9th, 2005. You can see Malfunction Junction was the worst on that particular day. But if you look in January, about a month later, you can see that the Reserve Street corridor had the highest levels. Most significant of all, though, you can see all these numbers are even below 3 parts per million. So we're well below the national ambient air standard of 9 parts per million, which is why Missoula has applied for maintenance designation instead of a non-attainment area. So we've had great success with that, and I think it shows that if we work at things, we can make some good progress. Particulate matter is a much more complex contaminant than carbon monoxide. Carbon monoxide is a single chemical compound, but particles can be made up of thousands of different substances. And they're sometimes unique to a particular geographic mix of industries and other lifestyle changes. They started monitoring PM10 in 1986, but by 1993, the American Lung Association said that the law wasn't protective of public health. Missoula could see that this was going to be up for tightening, so the Air Pollution Control Board passed new regulations in 1994 with regard to wood stoves and paving, hoping to start to make gains in reducing our PM10. The stations where particulate matter is measured around town are on the top of the health department building downtown and in Boyd Park, which is 4 or 5 blocks south of Malfunction Junction over by the YMCA. If you look at what happens to particulates during the day, this is a grid that shows the hour of the day on the x-axis, the day of the month on the y-axis. This happened to be for September 1992. The colors are such that the blue days are good days, and the more it gets orange, red, and black, the worse they are. You can see that our air was worse in 1992. These are some pretty high levels, but we noticed that you can see some periodicity to the releases of particulates. There's something we call the morning puff, which is where cars start driving on the streets and kick up dust that has settled out overnight. In the evening, when that cool air sinks and compresses and traps all the pollutants in the valley, we get the evening inversion increases in particulate levels. In between, we get the convectional uplift in the afternoon, and overnight we get dew out or frost out as water, when it condenses into water droplets or ice crystals, usually nucleates around dust particles and helps them settle. So we've tried to study the patterns and where these things come from. We've been doing better as a community with respect to PM10 since it first started being monitored in 1986. This is the first and second worst days. So you can see that since 1989 we've been pretty well below that, except we have a new wrinkle in the system. Forest fires in the summer have added some high days that we worry about now too. Although we don't have so much control over those. A lot of times the smoke comes from out of state, but it gets stuck in our valleys during the overnight inversions. We also look at the annual average. Here the national standard is 50, which is the first line below the top, and you can see we've been in good shape with respect to that since even back in the late 80s. The lawsuit launched in 1993 came to fruition in December of 1997 when EPA started to regulate smaller particulates, PM 2.5 microns or less. I'll put this up on the Air Toxics website so you can get this if you're interested in this information. So they felt that fine particulates posed a much greater public health risk than the coarse ones, so they added a new category. The EPA took about a year to design equipment and sampling methods, so the first compliance methods or measurements began to be taken in 1999. Here's what 6 years of measurements looked like. The initial standard was 65 micrograms per cubic meter on a 24-hour basis, and you can see usually we were below that line. And here was our annual average. There the value was 15. We had a little bit of trouble in 2000 because of forest fires. But we had some cold winter inversions too, so you can see mostly we were below the line. But compelling scientific evidence demonstrated that what they chose in 1997 still wasn't protective of public health. So last September, they had even more restrictive rules passed, and instead of having the permissible PM 2.5 level for 24 hours being 65, they cut it nearly in half down to 35. So if you look at that 6 years of monitoring data with the old standard versus the new standard, Missoula's in trouble. So we're above the standard fairly often. The regulation says that if you take a 3-year period, the 98th percentile reading must be 35 or lower. Since we measure PM 2.5 about every 3 days, we get essentially 1 day a year or maybe 2 above 35 and we're okay. Here's how 5 years worth of data look. Colored in red are the days that are above the level, and you can see that we're averaging more than 1 a year. So we're going to have some homework to do as a community to try to do better with respect to those small particulates. Our 3-year average between 2003 and 2005 was 46, well above the 35 that we're shooting for. We put this right into the EPA formula. So we'll be studying PM 2.5. Here's what all of the PM 2.5 data look like over the years. This is every 3 days. We'd like more more frequent observations. So PM10 acts as a way to look at sort of the same data. Here's looking at 2000 PM2.5 and PM10 overlaid on the same X scale. Or we can look at 2005. It's not always a simple relationship, but we're hoping to use all that data that you're collecting and that the compliance monitors are collecting to learn more about what's going on. Tony Ward has done a lot of sampling here in Missoula, and he found for the first time in his studies in 2000 that wintertime particulates were fundamentally different than the summer wildland fire particulates. In particular, ammonium nitrate becomes a significant contributor to the small particulates when it's cold outside. No one releases ammonium nitrate, but it forms in the air from chemical reactions that take place from other things that are emitted. Here was his pie chart for the year-round contributions, and you can see that ammonium nitrate was about 20%. He's just been doing a new study like this, so we should have updated pie charts maybe towards the end of the summer. I thought I'd show you what those secondary pollutants look like. I don't have ammonium nitrate that I'm going to show you because that forms at temperatures colder than in the room. It forms when nitric acid and ammonia mix. What I brought was hydrochloric acid and ammonia. These each release vapors that are invisible, but when the two mix, you can start to see some white particulates form in the air. That's the sort of secondary pollution that the ammonium nitrate makes. This material dissolves easily when we breathe it into our lungs, but it picks up other air pollutants in the air and delivers them all the way into the alveoli at the bottom of our breathing system. So that's not so good. So those secondary air pollutants are something we're going to take into consideration. Here you can see in Tony's work with anions and cations, ammonium nitrate came jumping out as big contributors. We also looked at organic chemicals that are in the airshed, and his study in 2000 included a forest fire season. What we found out was that in the summer there's lots of carbon-based things in the air. You can see the middle of the summer. This is January, or actually it's April through March. You can see the summer fire season there. So carbon was really loaded in during the summer months. But if you look at the suites of industrial and toxic sorts of chemicals that are released, this is the same year. The winter inversion had more of them. These are more related to fossil fuel emissions, industrial emissions. You can hardly see the fire season in the middle there. Aromatic hydrocarbons, which are part of fossil fuels, are released year-round in fairly steady numbers because we're so used to driving around. It's hard to even see the fire season. This is that same 2,000-year study. Can you see where the fire season is with respect to the aromatic hydrocarbons? These are the BTECs, which comes from gasoline, benzene, toluene, ethylene, xylene, and naphthalene, which is a marker of diesel exhaust. There's the fire season, so you can see our love affair with motor vehicles is there year-round. So if you're doing VOC sampling for us, you're picking up these sorts of things. I thought it was very appropriate if you looked in the newspaper on Monday. Page 3 had a big article that says, breast cancer strongly linked to common chemicals. So that list of VOCs that you're sampling for has been cited as being found in urban air and consumer products and real tightly correlated with breast cancer, leading cause of death in women in their late 30s to early 50s. So we need to make sure we know where these substances are found and how people are exposed to them. So those of you who are doing sampling inside your houses, that's an area that hasn't been studied nearly as much as the outdoor air. So you're really contributing valuable information for the overall growth of understanding in these sorts of exposures. So just wanted to let you know that you're a very important part of our team, and I'm looking forward to hearing all your presentations this morning. Thank you.
Okay, it's time. You guys ready? So we have a little different format this year than we had last year. And one of the comments from last year was that one school always gets stuck being last, giving blocks of presentations. So this year we've gotten a little bit creative and we've mixed it up. So we're going to draw randomly who's going to do presentations in a little while. But first we're going to have introductory presentations, one from Big Sky, one from Hellgate, and one from Corvallis. So I guess let's get started with Big Sky first.
Well, and actually, Tony, it might be good
And we're
to
gonna-
introduce our judges.
We are.
Oh, good.
And while Dave is loading his presentation, you may have seen some famous faces in the audience and moving about today. We are blessed to have a celebrity judging panel. And did I mention that we have Cold Hard Cash? Well, it's not really Cold Hard Cash. Okay, let's call it Cold Hard Cash for the best presentations per school. So best presentation per school, and then the best overall presentation gets an extra award. So these guys, this judging panel, will be the ones that are evaluating. I see some high fives in the audience here. So the judging panel, they're going to do a rubric. They're going to evaluate each one of your presentations, and we're going to tally the scores during lunch, and we're going to make announcements of the winners after lunch. Let me introduce the judging panel really fast, and Dave is getting ready to do his introduction, but really fast. You just met Garen. So, and Garen, are you Garen Smith or are you Gee Whiz right now?
I'm Garen Smith.
Okay. Gee Whiz will make an appearance in just a little while. So we have Steve Fetvite, and you might want to just go ahead and wave to the audience here. So you might recognize his face from TV, from KECI. He's the anchor, but he's also been the station manager for a long time in the past, and so he was back on the air in 2005 in September. He was recently honored as the Greater Montana Foundation and the Montana Broadcasters Association TV on-air broadcaster of the year for 2006. So congratulations, Steve. However, he's a graduate from Montana State. We won't hold that against you today. Thanks a lot for being here, Steve. So let's introduce Russ Thomas. He's an old friend of ours. This is his second time around on the Symposium judging panel. Chief meteorologist from KPAX, and he's actually a Seminole. He graduated from Florida State, and he got here in 2003, May of 2003. And I've actually had the opportunity to play softball with Russ a couple years ago, and he's a mean shortstop. So thanks a lot for coming again, Russ. We didn't scare you off last year. So next we have Heidi Miley. Thank you, Heidi, for being here. Heidi has an MA in Communications from the Edward R. Murrow School of Communication at WSU, Washington State. She has a BA in English Education. She's in a former life, she was a Seattle Seahawks cheerleader for 5 years. And she also has a claim to fame, but besides herself, she has a sister that won a gold medal in the women's standard position rifle shooting. Welcome, Heidi. And last but certainly not least, I was looking at a website last night. You might have heard it, www.airbergy.com. And I was thinking about a career change, you know. And so I'm looking at exactly what does an aerial freestyle skier do. So I clipped this from this website, www.airbergy.com. Another plug for you. Aerialists ski down a 25-degree in-run at 45 miles per hour and off a 14-foot tall kicker, which is the jump, that is 70 degrees at the top. The kicker launches us up to 60 feet in the air, where we perform triple backflips with up to 5 twists and quad backflips with up to 4 twists before landing on a 37-degree chopped snow landing hill. Piece of cake. Actually, Eric's a true American hero. Eric Burgess is here. He's a 4-time Olympian. He is, let's see, the list of accomplishments is pretty staggering here. So hopefully I can do him justice here. Let's see, gold in the 1998 Nagano Olympics and the 1999 World Championships, 2002 overall freestyle World Cup champion, 2-time World Cup aerials champ in 2001 and 2002. 15 World Cup victories to his credit. Ladies and gentlemen, Eric Burgess. So we're going to talk really briefly about what the judges are going to evaluate your presentations on, and Nancy Mara is going to talk about that.
Well, we were figuring with our panel of esteemed judges that we have all of our air bases covered, don't we? I mean, when you think about it, we have people who are on the air, right? We have people who are in the air, and we have people who are like studying the air all the time, and we have a wizard of the air. So we have all of your bases covered. Hopefully you've all gotten to see this, because this is what our judges will be using today. Have you all seen this? Okay. So very quickly, let's go over this so you can prepare and get ready. Our judges will really be looking for 3 things today. And you will be given a score of 5, 4, 3, or 2 according to outstanding, above average, average, and below average. And you want to represent yourself well because you've done a lot of hard work. But there are also prizes at the end, and if that's something that's important to you and you want to go for the gold, then let's go for it. And this is how you do it. First of all, you have to show that your research project has some meat to it, that you did your homework. Secondly, you have to give a very good PowerPoint presentation. So now today, just think about our keynote speaker when Dr. Garen Smith was up here, and think about his PowerPoint presentation. Our judges will also be looking for your graphics, your charts, the way you get your data across. And finally, you'll be judged, the third part will be your delivery to the audience. Can the audience hear you? Are you giving your audience eye contact? Are you getting the point across that you're trying to convey? Are there any questions about your rubric today? Then we'll go ahead and start with the introduction.
So because we're being filmed by MCAT, it's important to talk into the microphone whenever we do talk. And can't you tell Nancy was a teacher for 57, 63?
7 years.
Lots and lots of years. I'm going to pay for that one, aren't I? All right. So this is Dave Jones, high school chemistry teacher from Big Sky High School. And he's the one that we originally started the program with way back when. I went to graduate school with Dave here at the University of Montana long time ago. And he's going to give the intro for Big Sky High School.
Wow, you have no idea how amazing it is to see this place packed like it is. 3 years ago, was it 3 years ago? 4 years, yeah, 3 years ago, I think there were 6 of us in here. And it's great. I'm really excited about this. All right, so Big Sky's air toxics under the Big Sky contribution here is the Chem 2 classes. There are 33 of us, and we are mainly focused on volatile organic compound sampling. This year we focused on doing indoor-only samples. In previous years we've done both indoor and outdoor. There were 33 student homes sampled this year. We sampled once in the late fall, early winter time period. We used duplicate tube systems so that we were able to, through the analysis, actually replicate our samples. We did a 12-hour sample starting around 7 a.m. and going to 7 p.m. so that we had a picture of the time period during the day when the most traffic essentially happens. Our flow rate for our pumps were set at about 100 milliliters per minute, which gives us about 72 liters of total volume of air that is pulled through those tubes. And what this then represents is a kind of a chemical snapshot of what the air is like in the individual home at that particular time. The samples were then analyzed using a methodology called thermal desorption, gas chromatography, mass spectroscopy. And This is just a picture of the sampling boxes that we use. The tubes are the two top pieces there, and then the low-flow air pump is the little brown box in the middle. The sampling boxes had to be calibrated, and we had two very capable students doing it this year. This is not a picture of them, but this is a picture of a pair that was working on a couple years ago. And so each sampling box had to be essentially calibrated, and the flow had to be established prior to it going to the out in the field to be utilized. The target compounds that we're focused on were, there's 22 EPA target compounds, and I've just listed them here in no particular order. But these are all, in one way or the other, have some sort of health concern around them. Some of them are carcinogenic, some of them are just irritants, but the EPA lists them all as being compounds of concern. Okay. The other component of our project involved taking some GPS data points, and we just used an eTrex GPS unit. The latitude, longitude, and elevation for each home was essentially downloaded into an eTrex, and then that data was loaded into Veneer Logger Pro software, and then from that we used the Google Map program to produce the maps that you'll be seeing today. And the group projects, so we have 6 group projects total. Essentially, each group took the same data set and basically did a kind of a data mining where they looked at the data set and asked some questions about the air quality with respect to that data set, formulated some sort of hypothesis, came up with some sort of way to test that hypothesis, and then from that came up with some sort of conclusion. And so that's the basic format that you're going to see from the Big Sky students today. Thanks.
Okay, so Helgate, come on down, whoever's doing the intro.
All right, hello, I'm Brenna Wagner, this is Anna Marie Schober, and this is Paige Hall, and we will be introducing Hellgate High School's research of volatile organic compounds. So Paige will now cover what we're going to talk about in our presentation.
All right, first we'll go over the definition of what a VOC is, also our procedure and how we went about collecting data. We have a brief introduction as to what each of our projects will be covering, where VOCs come from in our everyday products that we use, safety precautions, health effects, and the common VOCs in Missoula.
So I'm going to give you guys a general definition of what a VOC is. And as we all know, VOC stands for volatile organic compounds, which are compounds that are emitted as gases from certain solids or liquids. And some examples of these include byproducts of household cleaning products and paints. And as Dr. Smith was saying, it also comes a lot from the cars we drive and the electric things that we use. And one of the main things that we're studying is that they may cause short or long-term health effects.
All right, so for each group at Hellgate, they all followed a similar or the same procedure for their data, and each group calculated the average flow rate for the sample run, and then they calculated the total volume of the air corrected through that same run period. Then they followed and converted the volume in liters to volume in cubic meters, and then divided the nanograms of each VOC by the volume of air in meters cubed. So that's their procedure that they each followed.
Okay, now we'll do a brief overview of each of the projects. We collected data of indoor and outdoor air, and everyone followed the same procedure.
So the first topic that was covered was how VOCs are affected by garages that are connected to homes as opposed to garages that are not connected to the house.
The next group studied if the age of a residence affects the amount of VOCs in a home.
They also did how do household populations affect air quality?
We also did what is the percentage of Missoulians that have asthma in relation to the quality of Missoula's air?
And the next was if a heating system of a house affects the air quality.
And the last one is, does the location in Missoula affect the levels of VOCs?
Now I'm going to tell you guys a little bit about VOCs and everyday products, and some of those include paint thinners and paints in general. They also come from the natural world, which is something that people don't think of a lot, but some of those sources are trees, termites, and cows. It comes from coal as well, plywood and other logging resources, adhesives, cleaning products, carpets, plastics, fabrics, and also, as mentioned previously, from our cars and the way we heat our homes.
All right, so some of the health effects that follow exposure to VOCs include irritation to the eyes, nose, and throat, nausea, damage to liver, kidney, and central nervous systems, memory loss, loss of coordination, and it's also a known carcinogen for animals and possibly for humans as well. And each of these health effects is based on the amount of exposure you have to VOCs and the exposure to which VOC you are exposed to.
For VOC safety, it's important to follow the instructions on the product labels. Always throw away your partially full containers or whatever when you're finished using them. Limit the quantities, like only buy the amount you're going to need. And then keep exposure to emissions low from products containing methylene, chloride, benzene, perchloroethylene. And with your storage, you also want to make sure it's covered properly and away from children and pets. And that also helps from these mixing. And you want good ventilation when using them. Industries are also trying to help lower the emissions by packaging their products differently and making it easier for the consumer.
And I'm going to cover some common VOCs that are found in Missoula and tell you guys a little bit about them. Tetrachloromethane comes from fire extinguishers and refrigeration, and it's very abundant right now due to its toxicity. Toluene, and I'm pretty sure I'm butchering that name, comes from gasoline, kerosene, heating oil, paints, and liqueurs. 1,4-dimethylbenzene is also another common one as well. Isopropyl benzene is that's a constituent of crude oil and refined fuels, which are abundant in Missoula. 1,3,5-trimethylbenzene comes from the preparation of distilled acetone. Benzene is another very common one, and that's an additive that's found in gasoline. Ethylbenzene is another common one as well, and that's used a lot in the makings of plastics. 1,2-dimethylbenzene, propylbenzene, and 1,2,4 and trimethylbenzene are also common ones, as well as chloroform, 1,3-dichloropropane. Once again, I'm probably not pronouncing these correctly. Trichloromethylene and chlorobenzene are also ones that are typically found in the Missoula Valley.
And that's it for our presentation. We hope you enjoy Hellgate's research.
Thank you.
Hi, I'm Kayla, and this is Kirsten and Kayla, and we're from Corvallis High School. And yeah, so the students from Corvallis High School, biology and chemistry class is who are doing the project. We collected samples of particulate matter in the air, and this is a picture of PM 2.5 right there. Some facts for you guys. Particulate matter is a complex mixture of minuscule particles made in acids, chemicals, and dust. PM can originate from volcanoes, dust storms, sea spray, and forest fires. The burning of fossil fuels or use of wood stoves can also produce high levels of PM. And this is a picture of what it looks like.
All right, a big impact of the PM amount around here is wildfires. And as you can, okay, the arrow, that's like our valley, and you can see it's really fogged up. So and when the PM amount increases in the summer, it's mostly due to wildfires. And wood stoves is the other main source of PM, and that's a picture in Libby of the wood stoves. And yeah, so when it increases in the winter, that's mostly why. Some facts about PM, like Dr. Smith said, the 24-hour standard is 35 micrograms per meter cubed, and yearly is 15. And 20,000 to 50,000 deaths per year in the United States are caused by PM pollution, so it's a big problem. Some other health effects: when you inhale excessive amounts of PM, it can cause cardiovascular issues, asthma, lung cancer, and death. And PM 2.5, which is what we're working on, penetrates the lungs and affects most of your organs and can lead to mostly heart problems. So this is another picture of like PM 2.5 is the little circle compared to like an average human hair. So it's like how they're teeny, so yeah.
Okay. We took the samples from students' homes, local businesses, and the air surrounding Hamilton. And we started in January and continued until May, just in students' homes mostly. And these are the pumps. And we took them to our testing sites and set them up in a commonly used area. Some people set them by wood stoves just to see what's coming out of them. We turned the pumps on, closed the case, and they shut off automatically after 24 hours of sampling. And these are the filters. Yeah. About them, the filters were sent to us pre-weighed from Chester Labs, and after testing them, we sent them to Oregon, where they were reweighed to find the amount of PM 2.5 in the filter. And
when we tested, we had to fill out a questionnaire just so we had background information about where you're testing. And some of the questions that were like important was how big the testing site was by approximate square feet, how much wood you use per year is really important, and like if you have a wood stove, like what's your primary heating source, and if you have like a whole bunch of dogs or no dogs, animals really affect it too.
So there were about 50 teens that did this project in 3 biochem classes. And so we hope you enjoy listening to their presentations.
Okay, so for our presentation, what we did is we did the study of carcinogenic volatile organic compounds in student houses. In our group, we have Dustin Moore, Lance Faust, Dylan Cato, Pachua Vang, and I'm Chris Ledger. All right, so for our thing, we tested the percentages of VOCs in the houses. We researched which VOCs were found as carcinogenics, and picked students who had unusually high concentrations of these in their houses. So when we looked for possible causes of these high levels, and we mostly focused on the compounds of chloroform, bromoform, and naphthalene. So what we thought or what we think that the carcinogenic VOCs will be found in homes, and that there will be some similar properties between each of the houses containing these compounds.
Okay, so the sources for the 3 chemicals that we picked, chloroform was found in manufactured goods and chlorination of drinking and wastewater, and swimming pools, pulp and paper mills, and hazardous waste sites and sanitary landfills. Bromoform was found in drinking water that was cleaned as well with the chloroform. It's also found in swimming pools and cough syrup. And naphthalene is found in gas when it's burned, and can be found also in wood and tobacco when it's burned.
So focusing on chloroform, bromoform, and naphthalene, what we did is we took our 5 top or 5 highest concentrations of chloroform, and then set them also against their levels of bromoform and naphthalene. You can see the levels of concentrations here, nanograms per cubic meter. As opposed to our students, the students are just given numbers, and those numbers are just basically their test tube numbers from their sets. Basically, just a quick map of where our students lived, from a couple out, from most of them in Missoula, one even all the way out in Lolo, just kind of a varying gradient.
These were some of our possible conclusions that we thought of. And a lot of them were on the city water in Missoula, so we contributed some of the higher level chloroform levels to that. One of our students lived near the pulp mill, Smurfit Stone, and that could be a possible thing for that. And that student also had a wood burning stove near it, and that could be a possible area for the naphthalene. And one of the main things was just the city water contributed to high levels. That's what we thought.
All right. Our final conclusion, with limited amount of data and test results, it made it very difficult to form or make any concrete conclusions. Going back to our case studies, we observed houses with the higher concentration of VOC levels, and they didn't tend to have any of the same properties throughout. And while some of the residences with high chloroform concentrations were connected to city water, many other houses also on the city water did not share any of these elevated levels. And we concluded that high levels could merely have been the result of an error in measurement, or may have been a bad data point that did not represent the house and its VOC sampling in terms of normal conditions. So further tests and more information about residences studied would be necessary to make accurate conclusions. Thank you.
And these guys will take questions if you have them.
I might ask you a question about chloroform from the pulp mill. Chloroform from the pulp mill used to be a problem, but not turning into a question particularly. But in 1999, they closed their bleach plant out of the pulp mill. We saw a 90% drop in the 90 to 96% drop in valley levels of chloroform. So I think the pulp mill is probably not a good source to consider in the future. What sorts of chlorine might be found in homes that could lead to your chloroform levels?
We really weren't sure. Mainly chloroform, we ended up, for the most part, taking it on ones we had a really high chloroform level, we call it city water, just using chlorination to city water. That also kind of for a little bit of bromoform, just coming off of that, with the air.
The reason we picked the pulp mill for an explanation for one is because the person that had it was relatively close to it, and when we looked it up on the internet for reasons why what chloroform was found in best pulp mills, I didn't look into actually Missoula pulp mill, so we just based hers on that because her levels were really high.
Well, that's the we couldn't find anything else to explain that. We spent the last period and a half or so looking over. We had students kind of little applications talking about their houses, the areas, and we couldn't find anything else.
We looked for stuff like new furniture or paint thinners or something like clothes, new carpeting or something, nothing came up.
So the pulp mill used chlorine to bleach the brown fibers to white. What in the house might you look for as a source of chlorine? Bleach. So that might be something to add to your questionnaire for future references, because if somebody does a lot of cleaning with bleaches, that could be a source of chlorine.
How
did you test your water? Did you set your things right by the water? Or did you just conclude that it was the water, even if you put it somewhere else in the house? How did you do that?
Well, with the, when we were testing the water, or when we were assuming that it's the evaporated water, because the water, if like it's left in the sink, it will evaporate, and then it gets into the air. So that's how we assumed that the chloroform that was tested in the air sampling came from the water supply.
So it was all based on assumption then?
Yeah.
The water was not actually tested. We did test the VOC sampling in the air. Basically, every room in your house can be susceptible to evaporation from your local water sources or
If you wanted to follow up on this, what would be a good room in the house to test for evaporation from water?
Definitely the kitchen or after the bathroom.
Why the bathroom? A particular thing that you find in the bathroom? Shower, there you go. That would be an interesting experiment, because if you think it's the water, test in the bathroom and run the shower.
Okay, thanks, guys. Okay, this is a Hellgate presentation.
Hello, I'd like to first welcome you all and thank the judges for taking time to evaluate our research. I'm Kyla Kenny, this is Lauren Dooley, and this is Emily DeWolf in Western Pelican High School. So for our research through the VOCs, we wanted to determine whether the location in Missoula affected the level of volatile organic compounds.
You guys heard it back. There you go.
Thank you. So,
Okay, for our hypothesis, we believe that people living in the downtown area and the more densely populated areas in Missoula would suffer higher levels of VOCs, and due to the high levels of traffic also. And Emily's going to talk about the variables that were introduced in our project.
So when we were doing our project, we had to think about a number of variables, those dependent, independent, and things we couldn't control, uncontrolled. With our independent variables, we had our areas around Missoula, which are displayed on this map. I don't know if you can see it very well. We had 7 areas all gridded out on this map. We tried to do it kind of based on population. The next independent variable we had was sample time, which is right around 720 minutes or 12 hours. We tried to do it from 7 a.m. to 7 p.m. Our dependent variable would be the level of VOCs we measured. We concentrated on basically 3 VOCs, which you'll see in our graphs later. And our uncontrolled variable would be the weather. It happened to be around probably in the winter and late fall when we were sampling, so we couldn't control if it was snowy or sunny.
I'm going to talk about our procedure for our project. First of all, we divided that map that I think she's passing around there into 7 different sectors based on population and based on area. So there is the upper Rattlesnake, lower Rattlesnake, Big Sky area, Sentinel area, all the areas in Missoula. And then we wanted to analyze the data that we got looking at the patterns of VOC levels. And we studied mainly just 3 types of VOCs so that we could narrow down our data. And we studied chloroform, trichloroethylene, and toluene in each area. And then we drew conclusions based on our data and recognized the patterns.
So, let's see, I'm going to stand over here. When you look at our graph of toluene, you can kind of see that all areas had higher level of toluene. This area, area 6, seems to be completely blown out of proportion. We thought maybe it was out by the airport, it's by the interstate. You can see area 6 on that map. And that had about 79,000 nanograms per meter cubed of toluene, which is quite a high amount. But you can see on the scale on the side, these areas that look small in this graph actually had around 2,000 nanograms per meter cubed of toluene. So that was one thing we observed. When we looked at the levels of trichloroethylene, we noticed that in area 1 and 6 we had higher levels, whereas in area 2, 3, 4, 5, and 7 they were lower. You can see our highest level was between 1,500 and 2,000 nanograms per meter cubed. See, with chloroform, we saw that area 6 again had really high levels of chloroform. Area 6 is kind of out past the airport, past Expressway, near the interstate and the airport and the Y. You can see these areas here, 7, 5, 4, 3, 2, and 1, have not even 500 nanograms per meter cubed of chloroform in them.
So after analyzing the 3 VOCs, chloroform, trichloroethylene, and toluene, we came to the conclusions that many of the homes in the more populated areas, or what we would assume more populated, densely populated areas, actually contained lower levels of these 3 VOCs. And there were high levels of toluene in all areas, but especially in area 6, which is less populated than in areas such as area 2 or area 3. And most rural areas, such as the Rattlesnake and Airport area, tended to have much higher levels of VOCs, or at least in these 3 elements. So based on these findings, we must conclude that our hypothesis is incorrect, that when pertaining to these 3 VOCs, the less densely populated areas actually have higher amounts than those that are more densely populated. Therefore, we must reject our initial hypothesis. Thank you. Is there any questions?
Remind me again of what type of sampling you were doing, the outside or inside?
It was all outside that we, we did, yep.
And what about things that were close to your locations in Area 6?
Yeah, we thought, well, Area 6 is right out here, so it's out past the airport and such. So we thought that the airport would then, be a big determining factor in that. And also the interstate runs right through our area. We also had much more limited samples from these areas. We actually only had 1 from 5, 1 from 6, 1 from 7. So it was really based on that one sample. So therefore, it would be hard to, really pertain that to the whole population. But, from that one sample, we were able to conclude that it was much higher than in areas such as 2, which were, the main university areas. Oh, go ahead.
Are there any service stations, or auto repair facilities close to your sampling site? Because those are usually real rich sources of those.
Yep, actually, right out by sample 6, there is a gas station right about there, and this one right out in the Big Sky area, that Mullen station, is that what it's called?
Yeah.
That gas station right there is real close. So that was another, one that you saw higher levels in area 7.
How many samples did you take in the other areas?
Well, we have about 4 and 2, 3 and 1. 2 and 3, 1 and 4, but we found the mean of them, so it's not,
All the data you saw on the graph was averages that are in different cells.
Why did you have more samples in some areas than others? Was that based on your original hypothesis?
Actually, it just kind of was how it worked out. A lot of students, since we go to Hellgate, a lot of us live in this university area. The people that lived in areas 6 and 5 and 7, that's not very common to go to Hellgate if you live there, so that's just kind of how it worked out.
And unfortunately, we didn't have access to the other schools' data, so this was just based off of Hellgate's data. So we were lucky, though, that we did have some people that were outside, the main city. So, yeah.
Why did you choose the group of chemicals that you did? Why did you think they would have?
We really saw the largest difference in them. A lot of the other chemicals, there was a lot of no datas or no reads, or they were all pretty standard. I mean, low amounts across, you know, the whole area. So these ones really jumped out for us, especially the toluene. We were really surprised on how high the levels were, especially in Area 6. So, I mean, those really were just the three that really jumped out and really, you know, although in the end didn't support our hypothesis, it still, you know, was very significant.
In the back.
Now, was this all in one sample day?
Pardon?
The samples, were they all taken on the same day? Or was it just one?
No. It was within a few months, winter time, but no, they weren't taken on the same day. So yeah, that was another factor variable that we had to consider. Sorry, we can't hear you.
So basically the data can't be directly compared to
No, yeah, that's one other thing we had to take into account was weather, you know, like all of the different accounts, because yeah, they weren't taken on the same, you know, 12-hour period.
Did you collect weather data at the same time?
We did, yep. Yeah, we have that, yep, on all of our data, but it is hard to compare when it's, you know, very different days, very different wind speeds, such, so.
Okay, good questions.
Anything else? No? Okay.
And we'll hang this poster up outside in the poster room, so.
We actually have a copy of this on.
Yep, it's on our actual poster out there,
Just
so.
draw what I just said. Okay.
Thank you.
All right, our presentation was on the woods and welding shop in Corvallis versus the average classroom, and we got this because I spend 3 out of 8 classes in the wood shop, so we were just curious how much more particulate matter I was in rather than that, I mean, compared to the average classroom. And so I'll give it to Mike and he'll start us out.
All right, so this is the shop, basically, the latitude and longitude, where it's basically located and its elevation. Yeah, go ahead. And so we predicted that the woods room would have like twice as much the concentration than the average living rooms of the students. And so we also predicted that the 3M filter would actually lower the concentration by at least 5 micrograms per meters cubed.
I actually messed up. Our original one was going to be to the average classroom, but then we changed it to the living room because we had more data so we could compare more. So that's my apologies.
All right, well, there's the living rooms. There's the results we got, the total collected, and the initial weight and final weight, and the most important thing was the concentration. So like 15.51, yeah. So the same thing for the shop with the filter, the air filter. We got all the results right here. The concentration being the most important again. All right, and this is the shop without the air filter, and so yeah. So yeah, as you can tell, it's way higher in the shop without the air filter. So I'll just hand this to Wes now.
Explain what the air filter was.
All right. The shop, the filter was placed up on top of the lockers. That'd be filter 1. And that was the first initial reading from the shop. Filter 2 was placed next to the 3M air filter, which we figured it would lower the readout from the shop. Okay, next. Here's the shop dust collector. Our shop has a dust collecting system so when you're cutting wood, it pulls up all the particles or most of the sawdust, and then also when you're welding, it'll take away most of the gas created by welding. This is a comparison on our 3M aero filter, and we actually brought our filter in the picture shown. And that's a new filter versus this one through the wood shop.
These filters are from a big filter. They filter the air and pump it back out into the air that you're breathing. This isn't the pump that made the data that we show you. This is just an air filter that they're not available in storage yet, but we were given. All right, here's our data, our graph of our data. We see with the average, we took the average of the living rooms, we took the concentration, averaged them out, and divided them, yeah, you know how averaging works, and it came out with a 15.51 micrograms per cubic meter. And then the shop with the filter, with the 3M filter, that filter is passed around right now. That was 141.367 micrograms per cubic meter. And the shop without the filter was substantially less. And we figured this out by accident, but we may have found a new experiment for later classes, which this one was a little bit less. If I can go back to the elevation ones. The one with the filter was right here, and it was lower down because we couldn't put it back up there because there's projects on top of the locker, and it was lower, so we were wondering if the height in the rooms was a little bit more, but we didn't have time to do that to see if it affected the particulate matter where it hung out in the air. But so that could be a later experiment. We saw, like I said, we saw from the data that the concentration did lower a little bit, but not substantially as much as we thought. And like I said before, we concluded that the elevation of the pumps could have, we guessed that it could have affected us in this, and if we had time, we would have experimented with that, but we didn't. These are what we could not control. We couldn't control the amount of wood because obviously students couldn't just be told not cut on their projects or whatever, and we didn't know how many students were in the shop. This is some stuff we could have figured out, but we didn't really want to right then. It's not that funny, really. And we also could have checked how many people live in the house and the pets and all that, but we didn't really want to get into too much depth and get ourselves in trouble more. So that's our presentation. Thank you guys for coming and judging us. We know it's taken out of your time of your work time, and thanks. Questions?
Looking at that filter, and you said when you handed it to Nancy that that's in a 24-hour average if it gets that dirty. Are those filters changed every day in the shop?
No, we just put it in there, and the teacher actually looked in 24 hours, and he saw that it was that clogged up, so we switched it out. That's just in the shop only, 24 hours with a big. It's a filter about this high, that wide. It's quite a big filter that filters the air. Yeah, like that. That's what it is. I didn't see that earlier, so. Any other questions?
Why did you decide to put a filter in the shop and not in the living room?
We actually had some data with the living rooms, but we didn't really know which ones were the separate ones, but we just, that's how it worked out. We were just curious if those worked that good or not. Any more? All right, thanks.
All right, I'm Max Showers, and our presentation is on animals and if they affect the VOC data, and household pets.
I'm Sam Jacobs.
I'm Job.
Okay, yeah, I'm Kyle Meyer.
And I'm Isaac Hampson. We decided to do this because after sampling, I noticed that some of the volatile air organic compounds in my house were had some raised levels, and there were a lot of different things that we could have tested, but we didn't have time to do another sampling, and so we went with pets because I have some big dogs in my house, I guess.
That affected it.
And we figured that that probably affected it.
Okay, so our basic hypothesis, as Isaac already covered, was we went from the assumption that animals with, say, shedding of dander, basic emissions of gas, whatnot, would probably cause an increase in volatile organic compounds. So our hypothesis works with that, saying that if the household in question has pets, then there should be an increase in the VOCs, not particulate matter, as is on here.
And to test our hypothesis, we took a survey of people who had pets and the number of pets and graphed it relative to their particulate matter concentrations. VOCs, sorry, excuse me.
And this is the result. Every rectangle represents the concentration of the compound in nanogram per cubic meter. And every last one represents the average concentration. As you can see, this toluene with the students that have pet, the average is higher, a lot higher than the student that don't have pet. And so it's the same thing. The average is higher. Next. It's the same thing with this graph too.
And the next one. And say it. Okay.
And so, in conclusion, we really didn't have enough solid data on the side of the households without pets. There's only 5 to average, but with the data we had, it was plausible because on toluene and a lot of the others, the average was definitely a lot higher, and you could see that. So, yeah. Thank you. Are there any questions? Yeah.
You said that the levels in households with pets was greater than houses without pets. Looking at your graphs, the bars look to be the same size.
It was a different scale.
Yeah, we just the scale. That was the.
So if you want your audience to pick up on that, you need to have the same Y scale for all your data sets so they can see that. I know sometimes Excel is not real friendly with how it, but just for picking up on your audience.
Yeah, thanks.
Definitely be a consideration.
Yeah. All right.
All right. Good luck, guys.
Okay, my name is Maggie Pizzanti, and this is Kirsten Thomas, and Sean Ray. And our group came up with the question, does the number of people in your home affect the amount of VOCs? And we predicted that, sorry about that. Technical difficulties.
I'm not against hearing the slideshow.
Okay, there we go. And our question that we came up with, well, our hypothesis, well, there's our question. Okay. Our hypothesis was the more people in the house, the greater amount of VOCs that would come out of that. And we predicted that because the more people, the more household products are going to be used, more electricity, and more cooking. And we researched the 5 most prevalent compounds: chloroform, benzene, trichloroethylene, toluene, and naphthalene. And Kristen will go into the information about those and where they come from.
Okay, so we've got chloroform, and a major use of chloroform today is in the production of Freon R22, which is used in refrigerators and air conditioners, and it's also used as a solvent and for producing dyes and pesticides. Inhaling vapors from chloroform can cause damages to the central nervous system, as well as dizziness, fatigue, and headaches. Benzene is most commonly found in cigarette smoke and natural gas, and it's also produced naturally by volcanoes and forest fires. Small amounts are used to make some types of rubbers, lubricants, dyes, detergents, and other drugs, also explosives and pesticides. And benzene is a carcinogen, so it can cause cancer, and too much exposure is very bad. Trichloroethylene is used in the food industry to produce coffee, to decaffeinate coffee, and in the preparation of flavoring extracts such as from hops and spices. It's also used as a dry cleaning solvent and as a degreaser for metal parts and stripping paint. And inhaling too much can result in a headache, dizziness, and an increased risk of unconsciousness. Toluene is very common. It's found in paint thinner, some rubbers, printing ink, adhesives, glue, liqueurs, tanning leathers, and disinfectants. And it's also found in gasoline, acrylic paints, and shoe polish. And inhalation can cause nausea and or irreversible brain damage. Naphthalene is used as an antiseptic and insecticide, and it's especially for mothballs. It's found in dyes and has been administered orally to kill parasitic worms in livestock. It can cause nausea, vomiting, diarrhea, blood in the urine, and jaundice, as well as increased fatigue and a lack of appetite. And that's about it.
Our procedure for finding data, we had 3 main steps. The first step was we found out how many residents are in each home. We found 7 people have 3 residents in their home, and 7 people have more than 3. We used the information from the data collection worksheets that the students took home to find out the amount of VOCs each person had. Then we compared the VOC levels between the 2 samples. We had, here are our variables, and our dependent variable was the amount of VOCs in each home. And the independent variable was the number of residents inside each home. And here's our data from the houses with 3 residents. You can see we calculated the averages at the bottom. And then here's the data with the houses with more than 3 residents. We did the same thing here. And we compared the averages in this chart. You can see that in benzene, trichloroethylene, toluene, and naphthalene, the numbers are greater in the houses with 3 people than they are in the houses with more people. And chloroform was our only exception to that. And here is our graph, and you can kind of see the high level of toluene in both samples. You can see there isn't a really direct correlation between the amount of VOCs and the residents in the home.
Okay. And our conclusion was not accurate. We predicted that the more people, the more VOCs. Actually, it was just the complete opposite. 4 out of the 5 of these chemicals, the people with less than 3 people had more or less VOCs, the people with more, 3 or more. And some further questions that we could have asked. Would a larger sample, we only studied 5 of these, and there's hundreds of VOCs in your home, so that could have caused the skew in the data. And Also, we just did it one night. We didn't, and they're at different times too, like September and October. And it could have been a different, if it were at a different time, it could have, we could have come up with a different result. And also, we didn't take into consideration the amount of pets in the home, the size of the house, the types of feeding, and those factors. And thank you. Any questions?
It's pretty comparable. Was it the trichloroethylene? Or was it significant?
It was the chloroform.
Do you have any to account for that, or any thoughts?
There was no real relationship that we could find between the two. In fact, the levels of the levels of the VOCs were pretty comparable, as our graph showed, between houses with 3 or more residents or houses with less than 3 residents. So we couldn't really find a direct relationship. So. Yeah, we didn't take a lot of variables into account. When we compiled our data, we didn't take into account the electrical or the heating or the number of pets or cigarette smoke. So there's a lot about our data that could be skewed, and more tests would need to be run. Yeah.
Do you think there would be any gender differences in the house population?
We didn't take that into consideration either, but I think that quite possibly there could be. Women have a tendency to use more electrical appliances for their hair, and also sometimes women tend to cook more than men. It just depends on the family and the way things are run. And more women in a house, more
also
hairspray.
The use of hairspray too. Really. So.
Yeah.
But you sample the garage for the guys.
Yeah, exactly, exactly.
That's a loaded question. All right. Thanks, guys.
All right. We're from Corvallis High School. I'm Jenny Hill. This is Chrissy Davis and Jennifer Marshall. We did how animals affect the air quality, and we tested several samples about from 50 homes, but we only took our data from the houses with pets.
Do I just push anything, or is it fine? Okay, so the purpose was to determine if indoor animals affected the PM 2.5 levels inside the houses or buildings. Oh, and our hypothesis was as the number of indoor animals increase, then the PM 2.5 concentration will increase too. In our procedure, the participants took home a pump. The pumps were set up in the most occupied rooms of the house, like the living room and kitchens. Every pump was ran for 24 hours, and the filters were sent to the lab for results. We took 50 pumps, or each student took, we had 50 students that took home 50 pumps, and we only took the samples that had animals in their house, and our sample period was from January to May. Wait, you're doing the maths.
This shows where all of our test sites were throughout, this is throughout the Bitterroot Valley. We had as far as not quite a little bit past Hamilton, probably by Scalcahoe, all the way up to Stevensville.
And as our results conclude, it shows that on average the PM 2.5 levels is associated with the number of indoor pets. And as the number of pets increased, so did the PM 2.5 levels also increase also.
All right, this graph shows the number of animals compared to the average PM concentration. And throughout we did, the first shows 0 animals, 1, 2, 3, and 4. And then on the y-axis, it shows the average PM concentration. And as you can tell, except for the houses with 3 animals, it steadily increased as the number of animals was larger. And the reason for there being a lower number on 3 is we had 1 test site, and that just so happened to be lower, and that we only had 1 because of errors from the filters. This shows the U.S. households with indoor pets. And the x-axis shows the type of animal, and the y-axis shows the number of households with these type of animals. And 2% had birds, 12% had cats, and 14% had dogs.
All right, and with our information, we were curious and looked up on the internet along with using Google Scholar.com to see if there were other experiments with PM 2.5 and with animals. And according to a study presented in the 14th IUAPPA, which is the International Union of Air Population Prevention Association, the only housing factor associated with the increased PM in homes was the presence of a pet. And the following doctors was J. Jones, S. Stick, P. Dingle, and P. Franklin. And we took in considerations of possible errors. Not all the pumps were run in the most occupied rooms, and the animal type or size wasn't taken into considerations. They just put down like how many animals they had of like indoor animals, and if any other air clean device was used except for the filters if they noted them. And several of our results when they came back from the lab said either there was a pinhole or scratches that were found in them. So we just omitted these from our results. And most of those were with the houses of 3 pets. So that's why we only had 1 result for those.
And we'd like to thank our judges, Heidi Miley, Steve Fetvite, Eric Burgust, Mark Haka, and Dr. Smith, and also our chemistry and science teacher, Mr. Hamill. Any questions?
Yeah, you can answer them. No, I don't want to answer them. Are you kidding me?
Got a question, right?
Yeah.
Yeah, all the pumps went out. We had about like 50 samples, but we only took the ones with animals into consideration and then put into our results.
Did you study results from the other pumps that were found, or why were they put out as well?
All the other pumps were used among our class, and so they all used those results too. So.
I was wondering, you said your sampling period was from January to May. Did you compare the homes that had a wood stove and a pet, or look at that at all? A home had a wood stove?
We didn't go over that. We were just trying to concentrate on the pets, and we didn't take into consideration if they had different heating devices like gas versus a wood stove, which is a wood stove would be much more, it'd put out a lot more PM.
So you said that you only used the data from those with pets, but on your graph you had 0 pets as one of your variables. So how did you come to that data?
No, we did use. They weren't in like the averages of all of our other results. They were just used as a standpoint for what the 0 would be. We didn't use it in throughout everything else. It was just as set as a level.
So if you were to guess, would cats contribute more PM or would dogs contribute more PM? I don't want to be trying to figure out which one to get rid of.
I would guess that it would be dogs, just because they're a bigger animal, and they tend to be less clean.
Probably like the dandruff and the other chemicals they carry on them. It could affect that, and they're larger. So, but.
We didn't study that though, so we could be wrong.
Just wonder about the litter box.
No, don't go for the litter box. We don't want that.
Okay, one more question right there.
Yeah, so one of the questions Wouldn't you be careful about letting just because of like most cats use litter boxes and stuff like that? If that makes no sense at all.
The cats.
And so, well, like also, we were thinking like maybe because you let dogs outside to use the restroom, they could carry them back in the PM levels from the outside, like gas and like fossil fuel burnings. So, and also like some cats are trained to go outside also, like what I have. So it depends, I guess, on the home. Any other questions? All right, thank you.
Right.
All right, thank you. Like you said, we're from Big Sky High School, and our main focus was geographical locations and their effect on geography. And we studied the...
Effect on air quality?
That's what I meant to say. Excuse me. And our... Wow. You got me. All right, so I'm Andrew Rosenbaum.
I'm Sarah Luscraft.
I'm Kenna Llewellyn.
I'm Kristen Hotchkiss.
I'm Anthony Ronaldo.
And I'm Jess Goslin.
Alrighty, so our question was what factors, as far as like location of different homes, would affect the air quality. And let's see. We looked at 5 main compounds in these homes, and we had 2 areas, right? Yeah, we had 2 distinct areas, 1.5 mile radius of each. And we had several waypoints or GPS points in each one of those areas. And we took data from those and compared the 5 chemicals or compounds and decided if the levels of those compounds were affected by the location.
So our procedure was we did our sampling first. We took our VOCs and each student took them to their house and put them in the largest room and did all the, what size is your room, the questionnaires and stuff. And then we took 2 distinct areas from Target Range and Mullen because those are the 2 areas that a lot of our Chem 2 students are from. And so we had a lot more students in those areas, so we took those 2. And then we drew circles in those areas because, radiuses because of that. And then our 5 most common compounds we looked for, which were benzene, toluene, ethylbenzene, 1,4-diethylbenzene, and 1,2,4-trimethylbenzene.
Get the map up. So our map should be coming up pretty soon. So this was our target range area. As you can see, we had 6 waypoints, and these are all within a 1.5 mile radius of each other. If we can pull a graph up, next slide. And the 5 compounds that we were looking at were all in relation to exhaust and car emissions. Sorry. There's the 1.5 mile radius. And this is our Mullen area. So you can see we had 5 waypoints in here, as you see, 2 close to each other, and then more further out Mullen Road. Where's our graph?
I don't know.
All right, we're having some problems with our graphs here. They're not showing up. We had one of our data pens stolen at the last minute or lost. We might not have all our data on this.
Okay, so I'll just talk about the graph. The data, actually, the averages were pretty close to one another. The only differences were in, I believe, ethylbenzene and 1,3,5-trimethylbenzene. But again, those differences weren't very significant. We can go back to the Mullen map. Just some factors that we wish we could have looked at. We only took in location, but there's a lot of contributing factors such as connected garages and other things that could contribute to the exhaust emissions. So these two homes are actually really close to a gas station that's right in this area. And what was actually surprising was on the graph you could see that waypoint 14 had a much higher concentrations of those VOCs than waypoint 36, I believe. And it could have been contributed to a filter in 36, or there's actually more cover from foliage for waypoint 36 as well. So in conclusion, there wasn't significant data to disprove or prove our hypothesis. Contributing factors, there was indoor sampling, so possibly outdoor might have been different. And older versus newer homes, it didn't seem to affect it either. And extraneous factors like I talked about, like connected garages, pets, etc. Thank you to our judges and our audience, and are there any questions? No? Okay.
We didn't have any questions.
Hi, I'm Nathan Cleddy. That's Dominic Goebel and Jacob Harrison. And our question was, does a garage affect the amount of VOCs present in the household? And our hypothesis was, if a household has a connected garage, then there will be a great amount of VOCs than a household without a connected garage. And our reason for thinking that was cars produce emissions that can be hazardous to the environment, and a connected garage will filter these hazardous emissions into the house, and also garages can contain paint products that release VOCs.
Okay, so our procedure, the first thing we did is we found out who had a connected garage, who didn't have a connected garage, and we did this from the questionnaire that everybody filled out. Then we converted our data to nanograms per cubic meters. And then we analyzed this data to find out a trend. We looked to see if there was a correlation between higher VOCs in the houses with connected garages. Some of our variables, the independent variable was whether the house had a connected or no connected garage. And then the dependent variable was the amount of VOCs.
All right, so this is our data from houses that had a connected garage. And I just want to have one spike that I want you guys to look at. It's right here. And this is for toluene, and it's a huge spike right there. And those couple of houses. And then next graph. These are the houses with no connected garage. And again, here's a spike for toluene. And for this one right here, for number 5, it's 1,3-dichloropropane. And there's 2 points that are really uncharacteristic with all the other 6 houses, or other 4 houses. So that sort of affects our next graph, which I'll show you. And here, the pink is with houses that have a connected garage, and the blue is with no connected garage. And you can see that for toluene, it's about 3 times greater in a house with a connected garage. And then right here for the dichloropropane, there's a huge spike for the no connected, which you can't really consider very valid, just because we have these 2 points that didn't go with any of the other points. So, yeah.
Okay, so since we saw a spike in toluene, we decided we'd research that and try and figure out why there's a huge spike. And we found it's a clear, colorless liquid with a distinctive smell. And it comes from contaminated workplace air, automobile exhaust, paint, and different paint products. Some effects, it can cause memory loss, dizziness, hearing, color vision loss, headaches, and it can affect your kidneys. And basically, it makes a lot of sense that a connected garage would be affected, with toluene would be affected and be higher in the homes because it's coming out of your car exhaust, and you also store paints and paint products in your garage a lot of times.
So our conclusion is that it looks like with toluene, how it affected it by about 3 times, that a connected garage does affect the VOCs caused by cars and cars emissions, but Connected garage won't affect any of the VOCs that are found in the environment, like pesticides and all that. So.
Okay, further questions that we could research. What other VOCs are caused by automobiles? We only had a certain amount that were tested, so we could do some more research on other VOCs. Also, another thing we could research is what caused House 1 and House 6 for the no connected garages to have such a high amount of 1,3-dichloropropene, while the other 4 houses had no amount. We weren't really sure what caused this. We'd have to basically do some more research on the houses and try and figure out a correlation. But for our purposes, we just kind of disregarded those 2 points because they didn't really have anything to do with connected garages and non-connected garages. I want to thank our judges, and do you have any questions?
Over there. Okay.
Did you take into consideration at all how many vehicles owned, and also what about people that use their garage more as a workshop and actually don't park their vehicles in their garage?
We didn't, because just basically it was due to lack of information. Every student was given a questionnaire, and it only had a certain amount of questions, and it didn't really go in depth. That would have been, if we could have had more control over that, that definitely would have been a factor that we would have considered.
Where were your pumps located? Like, did you actually test inside the house or inside the garage or outside?
Yeah, all our pumps that we looked at were the pumps that were inside the houses. So it was just like VOCs that were affected from inside the house.
You looked at all 21 VOCs? It looked like your x-axis on the graph was...
Yeah, there's 21, yeah.
Yeah.
What was your second highest VOC in the...
It was the 1,3-dichloropropene, but in all the other houses, like, it was really low to like none. So because of that, we just kind of disregarded it. And also, dichloropropene didn't really have anything to do with like car exhaust or anything. It had more to do with like farm fertilizers and stuff. So we figured that it might have something to do with where the person lives.
Did you compare the spikes to allowable numbers? Was there any EPA limits or anything like that?
What? Sorry.
Sorry.
Did you compare the spikes, the high numbers that you had, to any allowable limits or any concerns, health concerns in those homes?
Oh, no, we didn't.
Yeah, questions? All right.
Okay, I'm Amy Harvey, and this is Melissa Cousins, and we're from Corvallis High School. And we had one other person, Kylan Pelkey, but she couldn't be here. And we're doing PM Under the Big Sky, of course. And, okay, our purpose was to determine if there was a relationship between the daily recorded temperatures and the airborne particulate matter in Hamilton. And we just wanted to see how close of a relationship there was between the high and low temperatures and the PM 2.5 levels.
Sorry, can you hear me? Our hypothesis was that PM 2.5 would be higher during the winter months because it would be colder, so then people would be lighting their wood stoves, which would create the smoke. Also, PM 2.5 would be higher during the summer months because of the forest fires and the dryness. Temperature will clearly affect the particulate matter in Hamilton was our overall hypothesis.
Okay, and our procedure was we actually examined Hamilton's data because they have daily recorded temperatures and they do it daily, and ours were and they're outside in a parking lot, and from the samples we took at our school were all inside homes, and so it was going to be more accurate if we use Hamilton's data. And we created graphs relating the PM levels by date and the temperatures by date for a year and a half. And of course, there's not every day because some days the PM levels weren't recorded. So we have about 100 days, I think, yeah, that are compared. And yeah.
Some possible errors, like Amy said, some days didn't show up right with the PM levels, so we had to cancel them out of our graph so that our graph would show the highs and lows in the temperatures. Temperature variations were another factor. Dates of recorded forest fires. We weren't able to find the exact dates of when forest fires were started, and like was said earlier, there's a lot of forest fires from around other areas that the smoke came into the valleys and got trapped, so we couldn't record when that exactly was. And additional PM matter from other sources like pollen. And
another one is like in the winter, there's inversions and stuff, so it holds more PM in the valley, so it's kind of hard to tell exactly, but it's still obvious. So these are the PM concentrations by date, and you can see for the year and a half, we went from the beginning of 2006 to this May, or April. And so you can see that the PM levels went up in the spring, or in the winter when wood stoves were burning. And then in the summer season, in about September, early September, there's quite a few spikes in there, and then it goes back up in the winters again for big jumps for the wood stoves.
Here we put in the temperatures, and I think the red is the high and the blue is the low. And just to give you an idea of the median in between them, we didn't decide to do an average, we decided to show you both of them. And on the next, we put all the data together and we showed how the low temperatures, like in specific over here, you can see how the lower temperatures resulted up into a higher PM level.
And then also in the summer, you can see in these months when it went up during the forest fire season. So, yeah.
Our results, we found that our hypothesis was correct and that the weather did affect the PM levels. The temperature decrease, a direct correlation was seen between the PM 2.5 levels. This was due to the increase in smoke from wood-burning stoves.
And then when the temperatures increased during the summer months, the PM levels rose because of forest fire smoke. And of course, there could be some other factors which we couldn't take into account, but our overall correlation between the PM 2.5 and temperatures were correct. So, yes. And thank you for
Thanks for having us, and thank you,
yes.
judges.
So. Questions? Questions? No? Okay, good. Oh, yeah.
You said you took the data from Hamilton?
Yeah.
Do you know the number of wood stoves in that area?
No, I mean, because Hamilton, they don't record that. It's just the PM levels outside. Because our school was the ones who did like the wood stoves and the surveys, because you kind of have to survey to figure that out. So we weren't allowed to do. We didn't have that much data, so. Yep.
A lot.
Yes.
Yeah, it might be interesting to overlay precipitation data into your time series.
Yeah, I mean, that was another thing, because we didn't have time to do all of the weather patterns and stuff. So we just did the overall temperatures.
I'd probably pull that out of the newspaper.
Yeah.
Yeah.
Weather data.
Yeah, because I mean, we just did the highs and low temperatures. Of course, there's like humidity and precipitation and all that, but we didn't go that far. So, yes.
Any other questions? No? Thank you.
Thanks.
Great. Good job.
Our presentation, we labeled the danger zone, and we're with Big Sky High School. My name is Tana Getz. This is Megan Morrison, Sam Morris, Tyler Troutbridge.
Yeah, thank you.
Allison Huguet, and Lisa Devarskis.
Our question was, how does where you live affect the air you breathe? Some of our key focuses were we wanted to make sure that where we were living in our community, what we were breathing in, how is this affecting our health? Why we chose to do this project was we felt that everyone at Big Sky needed to know what they were breathing in to help with asthma, which is also a big problem in Missoula. Why is this important to our community? We felt that even if this became a more spread research project, that we would know more about what we're breathing in. Okay, next. Our research steps were we collected the data by our sampling boxes, and then we formed a hypothesis based on the data collected. Certain factors in the community affected the quality of what we breathe. Then we put the compounds and locations on the map, and then we connected the compounds to the locations. We also have a map that we'll show you, and then we formed a conclusion by those compounds.
Before we even looked at where these compounds came from, we went through and we just hypothesized what might be some possible sources for these compounds that we found with our VOC sampling. We thought unpaved roads, highly trafficked areas, Reserve Street, Malfunction Junction, potentially the lumber mill, and the compounds put off by the excess from that, the rendering plant, highways, the airport, and river pollution potentially, and trains also.
I work out. We researched 22 compounds, and the EPA says that these compounds are of special concern. We really focused it down to 5 of them: benzene, chloroform, toluene, naphthalene, and bromoform. Mainly because these were most prominent during our research.
No, I'm still on the last one. Okay, so as you said, we focused on 5 main ones. These we then researched to see where they came from. The benzene was produced by car exhaust, factories, water treatment plants, as well as landfills. Toluene came from car exhaust as well, but also came from gasoline and other fuels. The bromoform comes from chlorinated water, waste sites, and also factories. The chloroform was produced by waste and drinking water treatments getting chlorinated, and the naphthalene comes from antiseptics, insecticides, and comes from diesel exhaust as well.
Wait, are you done? Some of the important effects, which is what we're really wanting to focus on for the health problems that these compounds create. For benzene, breathing in high levels can actually result in death. It also causes drowsiness, dizziness, and rapid heart rate. Also tremors, confusion, and unconsciousness. And it can lead to harmful effects on the bone marrow, and it is a carcinogen, which is very important. As Dr. Smith was talking about earlier, this leads to breast cancer. Naphthalene is a hemolytic anemia. It can cause damage to the liver, neurological damage, and long-term exposure can also cause cataracts. Toluene, it affects the nervous system. It causes tiredness, confusion, weakness, and drunken-type actions, which we don't want any of that, kids. Memory loss, nausea, loss of appetite, loss of hearing, and color vision, and high concentrations can actually lead to kidney damage. Bromoform, it slows brain activities and causes drowsiness, and high levels can lead to unconsciousness and possibly death. Chloroform causes tiredness, dizziness, and headaches, and can damage liver and kidneys. It's also a carcinogen. As you can see, these are very serious compounds that we're dealing with, so we want to make sure that they're staying out of our homes.
So the map on the overhead represents all the areas in which we tested. We tested, I think, 33 sites in all.
The other map, which is on our board over there, has the points of interest marked out on it. We represented these by different colors of pins. The red represents benzene, the blue represents naphthalene, the green represents toluene, the yellow represents bromoform, and I think the black represents chloroform. So then she's going to go over the different areas of concentration which we found in our community.
The patterns on which you see here, the yellow, which is bromoform, is found on Reserve Street, which bromoform comes from car exhaust, car emissions. So that is really likely. You'll see that since Reserve Street has become compact with cars. We also saw the benzene is red, and that was spread, and benzene is from car exhaust also, and wastewater treatment, which is also by Reserve Street. And the railroads, you also found lots of chemicals that were used by the railroads, which is right along here and here. And then the compounds are mainly from car exhaust, which you see on Reserve Street. And this will also be in the display room, so you can come and get a closer look from it.
And for the judges' convenience, we have jokes pasted on the right-hand panel, if you'd like to read them. Who's doing the sites?
The sites affected most, like you will see on that graph, are homes by like high trafficked areas, homes by mills from mill emissions, airports, homes near where pesticide is used, and homes near large industries.
We also wanted to put pollution solutions as a part of our presentation. It's very important for people to be aware of what causes this and how you can fix it. Some things that you can do as just people who live in Montana and Missoula and the Bitterroot Valley is minimize your car use and maximize fuel efficiency. You know, try and break down your errands, make a list, only run a couple errands per week instead of running out, oh, I want an apple juice, and run to the gas station. Also, for air conditioning or different heating efficiencies, you know, do you really need that air conditioning pumping all the time? Keep in mind just gas efficiency in your car, rolling up the windows when you're going down the highway instead of, and then putting air conditioning on instead of having your windows down. Also, you can carpool, bike, walk, skip, whatever you feel like. Anything to basically break down your gas use. Energy conservation is very important. Basically, by that, we basically mean, you know, turn off your lights when you leave the room. Just things like that. I actually brought this up with my parents, and I said, hey, let's try doing this, and we brought down our electric bill during the winter by a lot. It was pretty impressive. Fertilizing naturally is really important. So instead of going out and buying a bag of fertilizer, you can maybe talk to your neighbor or their neighbors and see if they have any horse manure or something laying around that you could borrow. You can also reduce your pesticide use. There are all natural pesticides that can be used on gardens and such. Also, make sure you dispose of your waste properly. So you don't want to be throwing batteries away and different things like that. Keep in mind that landfills and factories do leach. So if you're going to be moving or living by a landfill and such things, you want to know where that is, and you want to be aware of the risks associated with that. And one more thing is don't burn plastics. They release a lot of harmful compounds into the air.
One of the main reasons we wanted to do this is to inform the community about pollution and how we can all change how we affect our environment, and we can all do our part in making Missoula a better place and a cleaner place if we all say maybe try doing a pollution solution.
And we just want to say thanks to all the judges and to our chemistry teacher, Mr. Jones. Questions. And any questions?
If you wanted to properly dispose of some of your hazardous chemicals that are left over, what would you suggest be done with them?
I believe you can contact your local, I think FBI. No, BFI. I knew that was wrong. Okay. Oh, geez. When I was little, I actually asked my mom why the FBI handled our garbage. So I believe you can contact them and talk to them either about arranging special pickups or can you do special drop-offs? I believe my dad does that. I don't personally do it, but when we paint our house and we use paint thinners and stuff, we do dispose of them using properly, I guess, a certain way.
That was a chance for me to give a plug for the annual Household Hazardous Waste Cleanup.
Ooh.
The Health Department and the Water Quality District specifically organized so September, look for the ads, and that's the proper way to dispose of your nasty chemical nasty.
Here we go. You say September? September. Okay, everybody, September. Oh, we already. Okay. Any more questions? Okay, thank you. Yeah, what do we do?
Alrighty, my name is Rhiannon Seaman. This is Brian Hickson, Kelly Barr, and Luke Baker, and we are seniors from Hellgate High School. And our project is on the percentage of Missoulians with asthma related to the quality of Missoula's air.
Our problem was how is the percentage of Missoulians with asthma related to Missoula's air quality. Our procedure was to analyze data collected from the university, collect data on respiratory problems, log the VOC concentration, and analyze the results. Our hypothesis was in Missoula there would be a strong correlation between high VOC concentration in homes and residents with asthma.
For our initial research, we wanted to see where the United States stood as a country in relation to the rest of the world in relation to respiratory problems. And we found a graph relating to adult respiratory distress syndrome. And as you can see, the United States is third highest of these top 20 countries. The first two are Barbados and Puerto Rico. And then from that, we wanted to analyze where Montana stood in relation to the rest of the nation in adults that had asthma. And Montana is actually on the lower end of the scale. We are the 5th out of the 51 states, including DC.
All right. And asthma, as we all know, is an affliction of the airways, which is characterized by an inflammation of them, where it makes it difficult to breathe. And this can be brought on by exertion or even contaminants in our air. And the three main VOCs that contribute to high-risk asthma patients are benzene, toluene, and ethylbenzene, which were all found in the tubes in pretty high amounts. And these can be found in everything from your furniture and carpet to household cleaning products, tobacco, and even if you wear Axe or Tag body spray, it goes there too. Oh, yeah. And the actual information we got from the university didn't quite give enough to really compare it to asthma, so we decided to call around. We called the EPA, we called the Health Department, the American Lung Association of the Northern Rockies, and we also called Diana Vanek and Ben Schmidt. And Rhiannon will talk about our results from that adventure.
All right, so we were in contact with, as Ryan said, multiple organizations, and we were unable to find any information pertaining to the percentage of Missoulians with asthma. So we decided to take results from our surveys from our classroom. And the first data analysis that we did was we just wanted to look at the overall distribution of the three chemicals that caused asthma. And we were just looking for any specific trends or patterns or extreme spikes or extreme lows in the distribution. After we looked at these 3 graphs, we took the 2 tubes that had the highest traces of the 3 chemicals in them, and we compared those tubes overall, and we also took the 2 lowest amounts of the traces and compared them overall. And in the individual tubes, we found that with the 3 highest chemicals, they were still the 3 highest as compared to each individual chemical, and even in the tubes that had the lowest amount of the 3 chemicals, they were still had the most amount found in each of those tubes.
In terms of what percentage of Missoulians have asthma, it's really difficult to find data for that. So we did find that 11.4% of all Montanans have asthma, or have been told by a doctor that they have asthma. And out of the 19 students that took the air filtration systems home, 3 of them had family members with asthma. The similarities between those homes, houses were older than 20 years old. All the homes had new carpet put in within the last 2 years. 2 of the homes had connected garages. All the homes used natural gas as a heating system. But there was no correlation between the levels of the VOC content with, or the highest levels and the lowest levels between the families that had asthma. So the differences we found, so there we go. And so in terms of what this data means, our research showed that there are specific VOCs that can contribute to an individual's risk of having asthma, but the data gathered from the air filtration systems failed to prove any relationship between the amount of VOCs in the home and family members who suffered from asthma. It was really difficult to find statistics pertaining to Missoula's county residents with asthma, which was our intention for this project, but we still believe that this is an issue that needs to be addressed.
Since our individual study didn't give any specific conclusions, we went and looked at other studies that they had online. Quit your giggling. Anyway, we got one from Perth, Australia, as well as one from Sweden, which pretty much addressed the exact same question we had. And in both of them, they give reason to believe that VOCs contribute to asthma and their problems.
Other possible contributing factors and ideas, the relationship between samples taken inside versus outside, the risk level of patients with asthma, like the intensity of the asthma wasn't considered, and the location of the samples taken around Missoula, as well as the different times of the year in which they are taken, like different weather, air speeds, and yeah.
That's it. Any questions?
We'd like to thank the judges, our teacher, and the community members who are involved with this project. And any questions? Thank you.
I am Cassie Gerber, this is Kathy Steinhoff, and this is Rose Wissenbach and Hillary Venema. We are doing PM Under the Big Sky, and what our project was, does age matter? And we're from Corvallis High School. And this is where we took our samples, is from the Bitterroot Valley.
Our purpose was to find out if the age of a home has any relationship with the air quality inside the home. Our hypothesis was that we believe that if samples are taken from houses of different ages, the newer houses will have a lower PM 2.5 level. Alright, our procedure was that students took the air pumps to their homes or other designated areas, and they filled out a questionnaire with questions pertaining to the building and its surroundings. The air pumps ran for 24 hours, then were brought back to school the next day for testing of the filters inside the air pumps.
Okay.
Our first graph that will be on the next slide has all the sampling sites and their PM 2.5 levels. The PM 2.5 concentration is measured in micrometers, and the age of the house is measured in years with all the graphs. As you can see, there's not really any relationship between all the different ages of the houses, so we decided to separate them into 3 different factors. We have the 3 graphs next. They'll be separated into 3 groups: those that had neither frying or baking occurring during that time or wood stoves, those that had factors such as baking or frying during the sample period, and those houses with wood stoves.
Okay, so in this graph, this is like the clean houses. This had no wood stoves, no frying or baking during the sample period. And you'll see that the newer that the houses, their PM 2.5 levels are lower. And then in the frying and baking houses, we got like opposite results. In the newer houses, the PM 2.5 levels were higher than the old houses. Yeah. And then in the houses with wood stoves, we had the same thing as the frying. The newer houses had a higher PM 2.5 level than the older houses.
Our results was that the graphs show that the newer clean houses had a lower PM 2.5 level than the old clean houses. And in the new houses with factors such as wood stoves, frying, or baking, the newer houses had higher PM 2.5 level than the older ones.
We have scientifically concluded that our hypothesis was correct to a certain extent. We decided that it depended on the insulation, because the newer houses are going to have newer insulation, probably better types of insulation than the older houses. The older houses would have had a chance to break down the insulation, would be more drafty. Therefore, the PM 2.5 in the clean houses would be able to escape or wouldn't be held in the older houses. And then with the frying and baking in the older houses, it'd be able to escape, which was why the newer houses had more. And
some possible errors we had was the amount of time the wood stove was used, and the amount of frying, baking taking place in the facilities, and also whether there were open windows or doors.
We'd like to thank our judges. Yeah. Okay. Any questions?
No questions?
Ooh, I guess we're good.
All right, thank you for this opportunity.
Thanks, guys.
Okay. I'm Kaylee Reed, and this is Amy Tana, Shannon Smith, Maya Lohr, Savannah Logan, and Amanda Gates, and we looked at the correlation of common VOCs found in car exhaust to the proximity of high traffic roads.
Okay, so the purpose of this project was to find a possible correlation between 4 chemicals which are all found in car exhaust, and these are toluene, benzene, xylene, and ethylbenzene, and these are not only found aromatic hydrocarbons found in the fuels themselves, but then they're also in the car exhaust when it comes out of the car. So our hypothesis is that the houses that were located the houses located closest to the high traffic roads would also have the highest amounts of these 4 VOCs. So our procedure involved acquiring the VOC concentrations from the various student houses. We also collected the GPS data points so that we knew where the houses were located, and then compared the proximity of these houses to the high traffic roads and attempted to find correlations between the presence of the chemicals and the high traffic roads.
All right, so this is like the first map section. We have 3 sections of our maps because we had so many spread out of the people's. This is everyone's data point. We tested 33 people, and so this is the first section. Go to the next one. This is out. Let's see. This is out North Reserve and Grant Creek, and you can also see Mullen. And then the next one is this is like the lower. This is out like Brooks and then down to Lolo. This is target range. Oh, and target range is up there. And then our next 2 slides, this one is, these are the samples that we took. So we found our first standard deviation of the average, which we found the average was 30,000 nanograms per cubic meter. And so then we took the first standard deviation of that. And so the range for that became about 2,400 to 58,000 nanograms per cubic meter. And so then any points found outside of that range would be the ones that we were interested in finding the correlation for. And so we found 8 points that were located out of that, and that's what these ones are. And then this next slide here. And also at the end of this, there's going to be another same 2 slides so that you can actually see what we're talking about. And so then we plotted these on separate maps like this, away from all the other data points. And we found that they were all located pretty close to either Reserve Street, Mullen Road, Lolo, or Grant Creek. And so these are all roads that are highly traveled on through Missoula. So Grant Creek and Mullen can really only be accessed by one way, and there are a lot of houses on each road. And so like Grant Creek, you can only go up North Reserve and you come back that way. So it's one concentrated area. And so as well as in the winter, Grant Creek Road, everyone's traveling up to Snowball. So that also creates an explanation for why that one has it. Go ahead. And this is just our conclusion too. 8, 11, 18, 19, 24, and 34 all were correlated together. Go ahead. And Lolo has the highway traveling through the town, and that's also highly traveled due to people coming in from Florence and Lolo who commit back and forth from Missoula every day. And then point number 22, which was the one that was way up Grant Creek, was kind of an outlying point. It was located so far up Grant Creek that there wasn't as much traffic, and so we thought that there was a lot less possibility for that much car exhaust to be up there. And so we decided that it was probably a different reason that one had such a high concentration. One of those could be like having an attached garage to their house, or there's multiple explanations, and we didn't go into any of that because we only had one high outlier, and then number 3, which was located out by Target Range area, was the only low one that we had. Go ahead. And so again, these are just our maps. So that's that high Grant Creek one up there that was way out from everybody else, and we decided not to use that other than it just being an outlier. And go to the next one. And as well as number 3, it's the low point. And so yeah, that was our presentation, and we just like to thank the judges and the audience. And any questions?
So we are the students against VOCs from Hellgate High School. My name is Gwen Evans-Lamayasfa. This is Nicole Holyoke next to me. This is Jason Barba and Joelle Rasmussen. Okay, so our question that we were asking was whether or not and how does the age of a residence affect the volatile organic compounds, VOCs? So our hypothesis when we asked this question was that as a residence ages, that the amount of VOCs present in the homes and the residence also increases. And so on the reverse, as a residence is newer and younger, it has less VOCs. We reasoned with this because we figured that newer homes have newer ventilation systems, thus being able to get rid of the VOCs within the home. So our procedure was that first we obviously sent home the tubes and collected the data, and then when we got it back, we analyzed it and did our calculations to get the desired label and everything we wanted so we could compare them. And we also had a questionnaire that had the age of the residents' houses on it, so we were able to create a graph comparing the age of the residents' houses and VOCs, which will later be discussed. So that was our presentation, and here are our quick calculations, which was also went over quickly in our introduction. So just so you can see, we used basic algebra and conversions, and we had to research certain conversions to get to our milligrams per liter.
This graph displays the total VOCs in the home. Most of our data that we collected was 40 years and younger. We only had 3 homes that were 80 years and older, so we didn't have much data on the older homes. This graph demonstrates or shows a 5-year-old home, and it doesn't have very many VOCs present. This is a 36-year-old home, and you can see a great increase in the amount of VOCs present. And this is a older home, a 104-year-old, and it has a lot less, but it still has a greater amount than the younger one. And this is Gwen's home. This was our outlier. She put in new carpet and has dogs and a connected garage. So she has a lot of good stuff in her home.
And so we picked 3 different chemicals, or 3 different compounds to compare, and you can see the age. You can see the homes, AT11, 1899, BS33, and Gwynn's house. AT11 is the youngest home, and then 1899 is the 36-year-old home, and then BS33 is the 104-year-old home, and then of course we have Gwynn's house. So you can see for chloroform there, and then benzene. The AT11, of course, has the smallest amount of VOCs, but then if you look at Gwynn's house and the 36-year-old house, and Gwynn's house is 12 years old, I believe, they're kind of equal, so we're a little worried about her. And then the BS33 house is 104 years old. So when you compare just the youngest home and the oldest home, you can see that our hypothesis is somewhat solidified. But here is a graph of all the residences, and you can see the ages of the homes to the right. And we have a list of 9 different compounds, and these compounds just kind of show our trend, our basic trend, and Nicole's going to be discussing that trend.
We found by analyzing our data and graphs that the middle-aged home actually had the largest amount of VOCs, followed by the older home, and then lastly the youngest home. We thought that one possible explanation for the increased amount in the middle-aged home is that it's getting to the point where remodeling may be needed. And in Gwen's case, they recently put down new carpeting, even though it's only 12 years old. But in the middle-aged homes, they may be trying to get rid of the old shag carpeting that was, you know, kind of cool in the 70s and 80s, and putting something a little more generic and lighter in. The glue and possibly even the matting underneath the carpet could have caused higher levels of VOCs in the middle-aged home. Again, with older homes, you may be looking at remodeling, and this could also cause the higher levels of VOCs. We did not consider some of the variables, including pets, connected garages, location of the residence, some refrigeration practices which can affect VOC levels, and again, construction, wallpapering, and carpeting. After finishing our research, we thought it would be really interesting to look at how remodeling actually affects how it affects the level of VOCs in the air. We also thought it'd be interesting to address how materials the house is made of may affect, as like the newer materials opposed to the older materials, newer filtration systems, insulation, as opposed to stuff that was put in homes 20, 30 years ago. We would like to continue conclude our presentation by extending a thanks to the judges for giving up their time to come and judge our presentations. We'd also like to thank all the students for attending and our chemistry teacher, Ms. Henthorne, for allowing us to participate in this project. Are there any questions?
That one is back.
Okay, in the back here. Okay, the question was, is there a reason why the older age house has higher levels of VOCs than the middle-aged home or the lower levels? And actually, we had to kind of hypothesize when it came to this subject, and some possible explanations were that, like, maybe in the 70s and the 80s, and they were building these houses with newer materials, moving away from the traditional just, wood, and moving into these newer, higher-end, maybe newly man-made materials, and so they weren't fully developed and they weren't fully fully studied. And then another possible explanation was ventilation systems and then carpeting. And also we thought maybe these middle-aged homes were getting renovated more often, as well as the older-aged homes than the younger homes.
You didn't include toluene in your graph. Did you see any patterns with toluene?
Actually, toluene was sort of incomplete for our data, so we weren't able to. The trend was the same, but we couldn't put toluene in our graphs because it wasn't really complete. Any other questions? Thank you.
All right. We're from Corvallis High School, and I'm Casey Burnett. This is Sunny Bleibtree and Michaela Hassenkrug. And what we did our project on is wood stoves versus other heating sources within the house and how it affected the PM level. And there are many various sources of indoor air pollution in any home, and some things that can affect the air quality are oil, gas, kerosene, coal, wood, and tobacco products. Also building materials, furnishings like cabinets and stuff, and furniture made out of certain wood types, as well as wood stoves.
Okay, our hypothesis is we believe that wood stoves do not have a significant impact on the particulate matter in the air. And
oh, my bad.
Okay, right here we have a graph showing the wood stoves compared to other heating sources. And in the dark purple is the wood stoves. And you can see that there's not much of a difference compared to the other heating sources. And when you would think that wood stoves would have a much higher. And we did this in micrograms per cubic meter.
All right, and then this graph we did was a burning day versus a non-burning day, in which, again, like where you would think like the wood stove day would be like where you burnt would be a lot higher, it actually isn't. And on the y-axis is micrograms per cubic meter, the concentration level. So there wasn't a significant difference. Our hypothesis was proved.
Okay, we did a t-test to show if there was a significant difference, because we could tell that there was a small difference, but we didn't know if that difference actually mattered. So according to the one-tailed t-test, our data has a probability of 0.16, which does not reject a mean difference of 0 based on a 0.5 rejection value. So basically this says that according to the statistics analysis, the houses with the wood stoves were not significantly higher than those with alternate heating. So our conclusion is that particulate matter in Bitterroot Valley homes was not increased by wood stoves. So our hypothesis was correct. And you go? Sure.
And some possible errors that we thought would bring into effect were the small sample size, the quality of the stove, and the number of pets in the home, and other sources of particulate matter, and the use of stove on sample day, where most, like if houses have moderate heating days or if they did not.
If they're frying and stuff.
Here.
But we looked over our questionnaires, and most of the houses that we tested did have moderate burning days, so they burned a normal amount of wood. So.
Isn't a difference between pets?
Yeah, but we don't
And
that's it. And that's all.
thank you. Any questions?
Oh, and thank you, judges.
Oh, yeah.
Gotta have that in mind.
Okay, thanks.
Okay, my name's Soren Estvold, and this is Kaylee Hasterlick, and we're from Big Sky High School. So our question for our project was, does the toluene level in a certain range correlate to the location of the sample size? And our hypothesis was the toluene concentration in a given range will affect the location of where the sample size were taken. Therefore, the samples in a given range will be found in the same general geographical area.
Our procedure was we were going to separate data into specific ranges, and we obtained the addresses, and then we obtained a map of geographical pinpoints of data using GPS coordinates. And then we would compare the data in each range to find any correlation between the toluene levels and their location.
So this is the main map that we made. And since our project focused mostly on the toluene levels, we went through our data sheet and we mined out the different levels of toluene, and then we gave them a color coordinate to correspond with those levels. So the darker the color, the like dark blue and the light blue, correspond to the lowest levels of toluene, whereas the green and the yellow correspond to the higher levels of toluene. And so, as you can see, there's higher levels in kind of the main Big Sky district area, which was just kind of the Reserve Street and just kind of that corresponding area. The lower levels were the more outlying areas, like the Lolo and Grant Creek area.
Okay, and because most of the students that we tested kind of lived in the Big Sky area, we concluded that there wasn't really much correlation between the ranges of toluene and the location.
So a more ideal situation for this kind of experiment was to, if we had, if we were to take samplings from different houses all around and not just where students lived, because the way we analyzed our data was just looking at those specific levels corresponding to where a student lived and not necessarily to where their location was.
We'd like to thank the judges and Mr. Jones, our chemistry teacher.
We did the air quality of wood stoves versus natural gas. I'm Heidi Hilliard. This is Michael Lanch, Laura Calderon, and Jessica Kilgore. And we're from Hellgate High School. Our question is, does the heating system in a house affect your air quality?
Our hypothesis is if a house is heated with a wood stove, the air quality will be worse than if the house were heated with natural gas heating system. We believe this to be true because wood smoke could contain more VOCs. Our procedure was receive data analyzed from the university. We created our hypothesis, examined the data, and determined what data would be used. And we made a spreadsheet and a graph which led to a conclusion.
Wait. Go back.
Just go up.
Okay. We focused on 5 main VOCs, and the VOCs that we found that came from wood stoves was ethyl benzene and naphthalene. And ethylbenzene can come from manufactured products such as inks and insecticides. And naphthalene can come from burning wood or burning tobacco. And then the 3 VOCs from the gas stoves are toluene, that comes from fingernail polish or adhesives, and chlorobenzene that is used to degrease automobile parts, and 1,2-dimethylbenzene that is commonly formed during forest fires.
I'm going to talk about our graphs. What you see on the top here, all our samples were taken from the insides of the home. Since you spend more time in the inside of your home, we figured that would be the place to look for the toxins that might be coming, or the VOCs that might be coming from your wood stove or gas stove. So trial number 1 here, the x-axis is the toxin number on the sheet that we had. We gave some to the judges here. But number 3 is benzene. Another spike that you see at number 7 there is toluene, which is from the gas stoves. Benzene is from both. If we look at number 8, 9, and 11 are chlorobenzene, ethylbenzene, and 1,2-dimethylbenzene. And then, not on this graph, but is a contaminant from wood stoves is naphthalene. Thanks. And then this is trial number 2. We had 2 houses that had wood stoves, and then we also had 2 houses that had gas, or we had multiple houses with gas stoves, but we chose to compare only 2, as we only had 2 with wood stoves. So as you can see by these graphs, it shows that there isn't much difference between the exhaust between a wood stove or a gas stove. And possible reasons for this are that a lot of people would think that a wood stove would be dirtier because you can see the smoke that's coming out, and a lot of the exhaust that you have off a gas stove is clear and you don't see it, so people tend to think, oh well, I'll get the pretty gas fireplace that you don't see the smoke coming from and it'll be cleaner. Next. So in conclusion, we found that the heating systems were very similar in conclusion with the other group up there. Therefore, our hypothesis was disproved. There isn't really that much of a difference between the two. That's it. Thank you guys, and thanks to judges, and let's go get some lunch. Questions?
I noticed on your graphs you use 2 very different scales, like one up to 16, one up to 18.
The deal with the graphs was that we had a lot of problems with Excel and different data that we gathered. A lot of the data we had, certain VOCs weren't represented very well, and then trying to alter the graphs to be similar was very difficult. Any other questions? Go ahead.
For your group and the other group, did you all consider the age of the wood stove?
We did not take that into consideration. We really didn't have that much data. A lot of people are using gas stoves now instead of wood stoves, and we only had 2 houses in our school that had that, and we couldn't find other data between gas stoves and wood stoves to compare. Okay. Oh, over here.
One of the questions that I should ask other groups that looked at this is your questionnaire tease out whether people use a wood stove versus a wood pellet stove versus natural gas?
No, we did not divide those out into the different burning systems. We just used wood stove, and I believe both of the wood stoves that we had were like cord wood stoves, not the pellet wood stoves.
There's a big difference on particulates between cord wood versus pellet stoves that I didn't know about the VOC.
All right. Okay, thank you.
So let's stay seated for just a moment. All of you had mentioned, all of you did a great job. That was a lot of fun. It was nice to see your presentation styles. It was nice to see that you had done some research. It was also nice to hear your good manners and to make sure that you thanked the judges As I was listening, I did notice that we had a little bit of confusion with the judges, and that's because of some things that we did. Meteorologist Mark Haka was not able to make it, so he was kind enough to find us people from his station. Heidi and Steve then came to represent the station. And then also Eric Fergus happened to be in town at this time, so that was very nice that he was able to step in. So I wanted to clarify who our 5 judges are, and just to make that clarification even bigger, and also to give them a big round of applause, because I think you all made mention about how busy these people are. We're going to call the people up, our judges up, and give them a little bit of a token of our appreciation.
Some of you may not know, I actually live here now. I retired from competition about a year ago, and I've had many opportunities to continue in my sport, coaching internationally, nationally, and even locally. But something has become way more important to me, especially in the last few years, and that is helping to preserve our environment and being involved in programs like this one. So I'm really happy to see all of the interest here, and I think everybody did a great job, and I'm going to spend the next year or so trying to figure out how and where I can help improve Missoula's air quality best.
I'll make this quick. I know you guys are hungry, and so are we, I think, everyone here. So anyway, I know just in watching this and seeing this last year as well, you guys put in a lot of time and effort in this, and you guys have other things going on in your life, and this is most likely extra stuff for you guys, and I think all of it, to me, looks very good. We're going to put together, I'm sure, numbers, whatever, and somebody's going to eventually win some kind of big prize. But in my opinion, everybody here did a great job, and you guys should be really proud of yourselves. That's it.
Well, I'd like to thank you all for being involved. You know, the world's just full of all kinds of challenges these days, and I think that it's encouraging to me, as someone who is now getting a little older, that there are young people coming up that are very focused on science, because I think a lot of the challenges in our world today can be met with good, solid science, and we can make a better world tomorrow. Thank you.
The thing I was impressed with was how you all came up and took part in your presentations. It's one thing to write an English paper or a science project and just turn it in just with your typing and your computer into your teacher, but when you all came not only to stand up in front of us, but all of your peers, I could see a little bit excitement in you. I could see a little bit of pride in your work and being able to show other people from other schools and your friends the work that you did and how proud you were of it. So I am just thrilled at how open and expressive you all are with your work. I was very impressed with all of that. I was critical of it in my writing, but that's because I think folks like you who can come up and do it, you know, can also improve it on the next level. But I was very impressed with you coming up and sharing your work.
I just wanted to add that now that you're initiated into doing air quality work, everyone in the community can take part in help forming air policy. The first Tuesday night of every month, 7 o'clock, down at the Health Department, second floor conference room, the Air Quality Advisory Council meets, and we love to have as many community members come and participate in those discussions and help do research projects for that group. So if you're interested in really doing some work in the community, first Tuesday night, 7 p.m., Health Department building, you can come work with us on trying to make Missoula's air quality even better.
So that you can all see what our judges are getting. They have a nice certificate and a nice University of Montana vest, and then these darling. Swear that's nice. Monty hat.
So we have 2 more presentations. One is from the Nez Perce tribe, and the second one is from Ember and Emily. You guys back there? Okay, I see you. So they're going to be up next, following a presentation from TUI here. This is kind of a natural extension of the Air Toxins Center of the Big Sky project, where we've expanded from air toxics into PM sampling and then using the PM sampling to evaluate different types of environmental problems. And one of the problems that we're facing is indoor pollution from wood stoves, which some of the groups addressed, and some of our data that we've shown has shown that there's a pretty dramatic impact on having an old non-certified, non-EPA certified wood stove in the homes. When you switch out an old polluting wood stove with an EPA certified wood stove, you get about a 72% reduction in indoor PM. So TUI is actually expanding on a program that's been done in Libby, where they've actually changed out 1,100 wood stoves. And this, so I guess it wrapped up last month. 1,100 wood stoves has been changed out in Libby, and hopefully that'll get them underneath the standard. We'll see this coming winter, but that was the goal anyways. This program that we have, it's an EPA certified or EPA funded program at the Nez Perce Reservation, where they're going to switch out 16 stoves. They're going to, we're evaluating indoor air quality before and after the wood stove changeouts. So TUI is actually, as part of the Northwest Indian College, he lives in Lapway, is the point person that's actually doing the sampling for PM. Next winter, next fall, we're going to train some of the high school students on the Nez Perce Reservation. And John is the outreach coordinator. Go ahead and raise your hand there, John. John is the outreach coordinator for the Nez Perce tribe, and will be involved with that as well. But let me, Tui's going to do his presentation. I've actually seen this in Reno, Nevada. There's a wood stove change-out conference, and he did an outstanding job. And so Tui's a semi-pro football player too, so he scares me a little bit. I'm not going to lie to you. No, he's a good guy. He's a good guy. He's, so he's got, this is his third time presenting this research, so Tui's going to take it from here. So Tui Maliga, he's going to talk about the Nez Perce wood stove change-out project.
Could we get the lights turned off first? Like you said, my name's Tui Maliga. I'm the intern for the Environmental Restoration and Waste Management Air Quality Program. Just a little background information on where I'm actually located. As you can see, located in the north central area of Idaho. Here's the territories of the Nez Perce reservations. You can see the purple is, I believe, the 1863 Indian Claims Commission territory. And let's see what color, the yellow, smaller, is the current boundaries of the Nez Perce Reservation. Here's the 5 counties located within the reservation that the tribe deals with. And here's a, do you have a pointer? Is that what this is? Okay, here's a topographic view. We're actually located around in this area. We're in a river valley, so we experience some of the same, call it immersions, as some of you experience with the being located in the mountain valleys. Here's a clear day from it's the Lewiston Valley here. As you can see the Clearwater River running through, but this is a fairly clear day. And this is a real bad immersion, morning immersion. It just shows you that there is a problem with air quality, and that's actually a paper mill, which many of you guys talked about in your presentations. And this is a picture of the Lapway Valley on a clear day, so the immersions can get bad. Here's some of our outdoor air quality sampling equipment. Hypothesis is the wood stove replacement will reduce indoor levels of particulate matter, or PM, and associated wood smoke chemical markers from domestic wood burning. Our partners, EPA, the Nez Perce Tribe, University of Montana, Northwest Indian College, the Nez Perce Tribe Distance Learning Center, and Institute for Tribal Environmental Professionals, or ITEP, which I was lucky enough to receive a short internship through. Our overview, we recruited the households. We wanted to conduct the sampling during the winter months of 06, 07 in 16 homes split between Kamiah and Lapwai, Idaho. We would wanted to actually do the change out this summer, but I think we've only finished 5 homes so far, but those 5 will get changed out. And we're measuring the ambient 2.5 mass before and after the change out. Measure the residential indoor PM 2.5 levels before and after, and do as much education and outreach as possible. The outreach efforts was, for recruiting the households was mainly done by Jana here. She did a good job, but I'm surprised we didn't see the numbers that we were looking for. She actually went to the local news station, did an interview, articles in the local newspaper, meeting with Nimipu Health, which is the local, I'd say, health clinic. She did a presentation for the Lewis Clark Air Advisory Committee, a tribal email through the Tribal Environment Education Group, and just interdepartmental coordination. For the ambient air monitoring, we wanted to utilize our existing network of equipment we already had. We had the 2.5 T-ohm, Met Tower, all this good stuff you guys will learn about later. See, the standards, as I've seen in a lot of the slides, for the 24-hour PM 2.5 went from 65 micrograms per cubic meter down to 35, and the yearly PM 2.5 is still 15. Our procedure, we wanted to sample for a 24-hour period for 4 sample days, and the equipment I used was the Leland Legacy sampler, the PEM, Personal Environmental Monitor, and a quartz filter, which see here, tests for organic carbon, elemental carbon, all this stuff. And I use a dust track, which is a continuous PM 2.5 monitor, and set that to run for 48 hours. And there was a health effects study attached to the paperwork that we asked the families to fill out. The health component is, as a participant in the wood stove change out, we asked the homeowner to take part in this study and monitor their asthmatic child's breathing using the PICO peak flow meter, which basically measures the child's lung capacity. Here's the actual meter here, and that's not a child, that's actually Jana here, right here. But she's demonstrating the proper way. On the sample days, I would enter the home, I would do an interview with the participant. I'd explain the study, the equipment, and like some of you may know that some of this equipment is annoying when it's turned on, but there wasn't no problems with that. I'd show them how to keep the records of their daily logs, collect their information of the home, the age of the home, square footage, number of rooms, the age of the wood stove, the wood type they use, cords burned per year, etc. Here's actually this here is the Leland Legacy, the PEM quartz filter, the dust track here set up in the home. My duties as far as taking care of the equipment, I would have to calibrate, set flow rates, clean, set up, take down, upload information from the dust track and email it directly to Tony. See, record keeping, document the equipment readings. Like I said, send the dust track files to Tony. Here's a picture of some handsome guy, hard at work here. And this is actually a graph from the dust track set for a 48-hour. This here should actually be 35. The 24-hour should be 35, but this is the yearly. But as you can see, there's these huge spikes in the graph of the reading of 2.5. And I found this interesting because 90% of everybody people spend up to 90% of their time indoors. And if we're breathing in this much PM 2.5 mass, it's really going to have effect on your health. Some more paperwork I asked them to fill out. They would record their home activities during the day, whether they cook, clean, burn candles or anything. Some Nez Perce traditional burning activities. The wood burning log, how many pieces of wood did they load, what time, and some of the challenges I faced was actually getting the people to show up on time to let me sample in their homes. That was one of the main challenges, and that's probably one of the biggest ones. Here are some pictures of the older wood stoves. As you can see, it doesn't look very healthy. For the change-out, we wanted to provide and install up to 16 EPA certified stoves. Which give off less emissions. We wanted to work with the Tribal Employee Rights Office to possibly get tribal members certified to install the stoves instead of going out of community to hire on an installer. And did a lot of work with the Libby, Montana change-out folks, and mainly Tony Ward was a big help. Education and outreach, we wanted just the general public to know the health effects of wood burning stoves, how to operate their stove so it burns more efficiently, asthma, smoking, and indoor air quality. Northwest Indian College student presentation. That's work with the tribal programs, wood delivery, housing, early childhood development. It's sort of a preschool. We wanted to actually go into there to try to catch some of these kids with asthma before it can get worse, in community events and going to the schools. Here's some preliminary results from Libby. As Tony said, the average reduction in PM was 72%, and I fully expect that our results will be similar to this. And I think it was Tony who was saying that if the level of PM goes down by up to 72%, that should overall raise your health by the same percentage. That was it. Any questions?
Does the EPA pay for the stove? Is it any cost to the homeowner?
No, it's they pay for the old wood stove to get taken out, and it's a whole complete system: the stove, the pipes, the flue, everything.
There's no cost at all.
No.
Was it that way in Libby too, Tony?
The Libby situation was there were low-income homes. There was a free change-out program for an X number of stoves, so they would provide that way, and then for the rest of the residents, it was like a 50% share, so you got a voucher for X amount, and then that, they were good for wood stoves, pellet stoves, wood burning furnaces, all those kinds of appliances, so they were kind of 50/50 split thing with EPA. Well, and actually part of it was the barbecue folks, Tony can tell us about that, that provided, the people, the wood stove industry people have provided a significant amount of help in all that as well.
At the Hearth Patio and Barbecue Association, that's a trade organization for all the wood stove manufacturers in the United States. We call them the Barbecue Boys. They funded the Libby wood stove changeout program. Partial funding, EPA funded some, and then Conrad and Burns had earmarked for Libby.
It was 1,100 in the beat.
1,100 stoves were changed out. Old floating wood stoves changed out with EPA certified stoves.
I just want to congratulate all of you high school students on a job well done and keep up the good work.
So this is the second go around for these guys. They're Big Sky seniors now, and they're short timers. They're also going to Montana State, Steve. So, but they were the stars from last year, and we liked them so much we brought them back this year. So they have done some special research sampling with the particulate matter using these filtration units provided by 3M to evaluate these filters in homes with wood stoves. And I'll let you guys take it from here. So Emily Kobos, Ember Hansen, Big Sky High School.
All right, well, a big thanks to Tony. Like Tony said, I'm Emily Kobos, and this is Ember Hansen. And our project essentially was to test these 3M filters that we were given to check the efficiency and see how much of a reduction in particulate matter they actually provided the home. So essentially what we did was we had 2 sampling setups before and after with the filters. We did 48 hours before we placed the filter in the homes. And then we brought in 2 3M filters to each home because the rooms were so large and the filters are only designed to cover a certain amount of square footage. So we placed 2 within those rooms and then did another 48 hours of additional sampling with the dust track monitor, which is a continuous PM 2.5 monitor, and found the % reductions.
Okay, this was our first home. And as you can see, these are just readouts from our dust track that we actually used. Keep going. Okay. Does this thing work?
Yeah, that way.
Oh, yeah, okay. All right. So, like I said, this is our first home. And you can see these spikes right here. And actually, what these are is when the people opened up their wood stoves to restoke them or rekindle it. And it's pretty interesting to look at because they shoot up really rapidly, and then they just kind of taper off, and then they're hanging out down here, and then they shoot up like really high again. And actually right here, I don't know if you guys can see this, this area right here, we asked the participants to keep a log of the activities in their homes, such as vacuuming, which usually kicks up a bunch of dust and particulate matter. Also like frying and baking and cooking and that sort of thing. And it was funny because we saw this and we were like, well, what could account for this? And actually they were cooking and they burned something and it was just no good. So that was pretty interesting to see.
So these are the post-filtration unit PM graph from this particular house, and as you guys can see, there is a huge reduction in the amount of particulate matter and in the spikes as well. There's only one baby one over there at the front, and I believe at this house it was a 50% reduction in PM with the air filter. And this is the preliminary data from the second house. Again, the spikes are from the wood stove being opened and closed, stoked, reloaded, some of the other activities in the house. This one's a little all over the place. And this is the post data. And again, it's a huge reduction in the PM. And with this particular house, we had actually a second day worth of post data that is shown right here. And the scale on this particular graph goes up to about 1.4, whereas the others have been around 0.045, 0.055. And this particular spike was caused by a huge plume of black smoke that came out of this family's wood stove. So kind of threw a glitch in our data, but once we removed this outlying spike, there was a 40% reduction in particulate matter from this house as well. So I think that is all we have for you guys. So thanks for listening. Do we have any questions? Yeah.
I was trying to follow the date and the month. Was it around the same time we did the filtration system?
Yeah. We did both houses during the winter when the wood stoves were being used the most. In both these houses, actually, the wood stoves were a main source of heat too. So, yeah.
Do you know what the filters cost?
We'd have to ask Tony on that one.
They're actually not on the market yet, so I don't really know what retail value might be, but
They're going to be about $250, $300.
Just a follow-up, Tony, you saw a 70% reduction indoor.
When you change out an old gluting wood stove with an EPA certified wood stove.
Could you assume the same number for the outdoor PM change? As
You
far as
have to change out a lot of wood stoves to get that.
Yeah, but going up the stack of that particular stove, would you expect?
I don't know.
Is there correlation between indoor and outdoor?
Be something interesting for you to look at next year.
So your dust pack data shows some big spikes, which would be sort of an acute exposure. Are the reductions that you're expressing, are they drops in what that acute episode would be, or are they an integration underneath the curve of the total particulates that are released into the house?
I believe that they were overall reductions. I mean, in integration reduction, as opposed to just a spike.
And I think it's actually important to look at both acute exposures
Right.
as well as total and chronic sort of exposures. So it might help in your presentation if you make which kind of reduction was measured there.
Yeah.
How often would you have to change the
I'm not really sure. This was we ran for 4 days. We ran, 4 days in each house. And actually only 2 of the days in each house had an air filter in them. I don't know, it'd be interesting. It'd be an interesting project to see how long you could run a filter for. Are there any more questions? All right, thank you.
So, and this is important too, because some of the other research, and Curtis Noonan, he's an epidemiologist that I work with quite a bit, he was here earlier. So we take this information, we're able to, if we remove a wood stove, you get a dramatic reduction in PM. You put in these filtration units, you get a dramatic reduction in PM. He looks at the health effect of asthmatics in these homes, that live within these homes. So one of our next research projects is to see if the asthmatic conditions actually improve as a result of cleaner air quality. So it all ties in together, and you guys are helping make that possible, looking at the health effects and improving the health effects as opposed to, or being exposed to air quality, poor air quality. So with Corvallis leaving, the next planned agenda is to recognize the teachers for this study. And without you guys, this wouldn't be possible. So let's have Dave Jones come down. Brock just left. Is Melissa here? And Rochelle Troiano, who's the teacher at the Northwest Indian College, is not here. So let's have Jonna come down as the stand-in. All right. Okay. So first up is Dave Jones. I think it is mandatory that he must put it on, so. All day.
Yes. Wait.
Got built.
Could be a lot of work to get those things on. All right.
Have some pom-poms.
So Brock Hamill just left. He was the teacher from Corvallis High School. He's actually a new teacher there this year. The ex-teacher, I guess, Jim Strevel, went to Rocky Mountain Labs. So Brock took on this whole program and started this year. So this is his first year of the program. And I just like to recognize him for doing a great job, even though he's not here. So, Brock. Melissa Hinthorn, the teacher at Hellgate High School, and this is Melissa's third year in the program, and she's done an awesome job with the program for the last 3 years, and we certainly appreciate everything that she's done. You don't have to wear the hat. You can if you want to. Let's put it up to your students. Do you want Melissa to wear the hat? Okay, and then Rochelle Toronto, who is actually the new teacher that took on the program this year at the Northwest Indian College, the Distance Learning Center in Lapwai and Kamiai in Nez Perce. So Jonna is actually the stand-in for Rochelle. She's
Do I get something for standing in?
You do. You do. So, thanks, Jonna. And we're actually going to work with Jonna next year in recruiting high schools on the Nez Perce Reservation and taking this program to the high schools on the Nez Perce Reservation. So, thank you, Jonna. Now, we have the results of the best presentation per school. And Melissa and Dave, if you would stay up here just for 1 second. So Corvallis, the best presentation for Corvallis was actually being presented right now. They had to leave at 2:15, so they weren't the grand prize winner. So actually the grand prize winner came from either Hellgate or Big Sky. So these are actually gift certificates, or not gift certificates. They're less than that. They're just recognition certificates. They're not really gift certificates. Sorry. Unredeemable. For you guys, and we certainly appreciate you guys, collecting samples and coming today and presenting your research. Just wanted to recognize a couple of people. The Center for Environmental Sciences, who co-funded this project, Montana DEQ, and Bonnie, I think, is gone. EPSCOR, NIH helped fund this program, 3M Corporation, and without further ado, let's announce the results. So for Big Sky High School, the best presentation was?
Danger zone. The danger zone.
Danger zone. We'll also thank MCAT, Ron Scholl, EPSCOR, Justin Lee, Holly Truitt, Gay Allison, and DQ, 3M. Paying the bills. So go ahead and announce your names.
I'm Tana Getz.
I'm Tyler Trowbridge.
I'm Elisa Dvarskas.
Sam Morris with 1 O.
I'm Allison Huguet.
All right, and what'd they win?
Should I say?
Pom-poms.
Pom-poms. $150. And a gift card to the bookstore at the University of Montana.
Yeah.
Yeah.
All right.
Yeah. I'm going to shake your hand.
Sure.
Thank
All right,
you.
great job, really.
Thank you.
Yeah, good job.
Thank you.
Good job. Good job. The first place for Hellgate High School
Sean, Maggie, and Kristen.
is
First place, Sean, Maggie, and Kirsten.
Good job. Good job. Good job. And you might as well stay up here because I think the grand prize winner is from Hellgate.
Emily, Laura, and Tyler.
And this for Tui, and then one of these, I don't know, Michelle had one. Do we need a microphone?
Video, Maggie. Photo opportunities.
So let's hear it for the grand.
Photo opportunity for the grand prize.
What did you guys win?
I really can't get it open.
Yeah, one bad enough.
Well, $200. So,
All right.
thank you.
Big bucks. So I didn't see who were the winners from Big Sky then. Excellent. And we had to have Corvallis go out of the room with us to catch their bus, and they had a first place winner from Corvallis too. The one about does age matter was the first place winner from Corvallis. Have you had fun today? Yeah, it was a very, very good day. One of the things that's important to us is to be able to continue to offer this to high school students and now bringing on college students as well, and to continually get better.